Hello students, this is your friend Sumit and today we are going to discuss topic 11 of the series, that is gravitation. Gravitation is the topic which is having 70% similarity with electrostatics. The derivations which we will do here, the formulas that you will see here, you will see a very much similarity which what you have understood or will be understanding in electrostatics. Okay, so many of the things will feel like as it is. Okay, the same things, the derivation that we do here for the field, for the potential, the same type of derivations we do there for the field and the potential and the other things as well. Okay, so when you will watch this video, you will feel like you are revising electrostatics. Okay, many of the topics of this particular chapter are very much asked. If I talk about let us take gravitational field or satellites or Kepler's laws, gravitational potential, these are the topics which are very much asked. Okay, so in this video I'm going to cover each and every detail of this, what is asked by NTA and that is expected in 2026, the varieties of the questions, everything you'll get. With that, you need to practice the questions yourself as well. You'll ask, sir, from where I can practice the questions? I have a good set of collection for you. In the description, you click the link, you'll go to the PW app, and PW app is the only platform which provides quality teaching at affordable prices. As you know, from there you'll get the notes as well as the DPPs of this video and you can have your practice from there. Okay, so let us begin the discussion. We'll be covering entire details of this particular chapter. I have mentioned few of the major topics. First of all, we will be talking about Newton's universal law of gravitation, then about gravitational field, acceleration due to gravity, potential energy and potential, escape speed, then satellite and Kepler's laws. If you talk about the most important topics among them, I will say gravitational field is very much asked. Acceleration due to gravity is also very important. Okay, escape speed, satellite questions are also asked, and Kepler law questions are also asked, and other topics are also. So I will say this topic is not very difficult, and as I already mentioned that it has a very much similarity with what you have learned in electrostatics. Okay, so many of the things are quite the same. So let us begin with the first thing, Newton's universal law of gravitation, which states that two masses, let us take this is m1, I'm considering point masses, okay, m2, they are kept at a separation of r. The force between them, they will attract each other. Like in electric charges case, there were positive charges as well, there were negative charges as well. Opposite charges will repel and similar charge, you can say opposite charges will attract and similar charges will repel. We have understood that concept, but in gravitation only attraction will be there. Okay, no repulsion is there, so only attraction is there, so they will be attracting each other. So if I write the force on 2 due to 1 and this is force on 1 due to 2, both the magnitudes of the force will be same. Okay, if I say the magnitude of these forces, it is the same. So if I just write in terms of magnitude, I'll say this is F and this is also F. In terms of magnitude, when I say, I'll say this is F and this is also F, because the magnitude is the same. And what is that? G m1 m2 divided by r square. So you can say the force depends upon the product of the masses, inversely proportional to the square of the distance between them, and this is our proportionality constant, which is G. G, we say this is my universal gravitational constant G. Okay, and what is the value of this? That is 6.67 into 10 to the power minus 11. And what are the units? F is Newton, so I'll say this is Newton meter square per kg square. Newton meter square per kg square. Okay, so this value you need to keep in mind. Now, if I say this is my force on 1 due to 2, this is my force on 2 due to 1. They have the same magnitude, but the direction is opposite. Okay, magnitude is the same, but the direction is opposite. So in vector terms, when I say F12 is just the opposite of F21. Magnitude is the same, but the direction is opposite. M2 is being attracted by M1, so its direction is towards M1. Now, this M1 is being attracted by M2, so its direction is towards M2. So, if we see the direction of this force F12 is opposite that of F21. In gravitation, always the force is attractive. In electrostatics, we need to see whether this will be an attractive force or whether this will be a repulsive force, but here always attractive in nature. Okay, so if I draw the forces in vector form, okay, let me draw the axis first. Let us take this as my x-axis, this as my y-axis, I'm having 2 point masses, M1 here, M2 here. Okay, so let us draw the position vector for M1 and M2. So I'll say that let me take this color. So this is the position vector of M1 and this is the position vector of M2. Is that clear? Now, if I say this as my R1, let us take this is my R1, position of M1. This is my R2, position of M2. Now, if I ask you, what is this vector in terms of M1 and M2? In terms of R1 and R2, what is this vector? Now use triangular law of addition. See, this vector plus this vector is equal to my R2. So if I ask this vector, I'll say this is my R2 minus R1. Getting it? So this vector is R2 minus R1. And this becomes my R21. What is the direction of R21? Towards the right here. Okay, in this direction is my R21. Now, I am writing that force in vector terms. So, if I write force on 2 due to 1, force on 2 due to 1, we know that is in this direction. This is my F21. Okay, so first of all, let us put the magnitude of this. What is that? G M1 M2 divided by the distance square. What is the distance? R21, the magnitude of R21. Okay, so R21 square. This becomes my magnitude. Now I need to give the direction. How we give the direction? By multiplying it with a unit vector. Unit vector means a vector divided by its magnitude. This is how we get the unit vector. I need vector in the direction of F21. This. What is this? This is opposite of R21. So I'll say this is my minus R21 divided by R21. Okay, so this becomes my minus G M1 M2 R21 divided by R21 cube. This is my F21. And if I need to write F12, I'll just say F12 is just minus of F21. It is equal and opposite. The same exercise we did for electric charges also when we were discussing Coulomb's law. Okay, we put two charges, we draw the position vectors, and then we wrote the forces like this. Now, let us do some questions on this. Now we are having, although this is just a formula, okay, there are questions directly based on this. You see, just simple question, and this question was asked in 2022. Let us read it. Two objects of equal masses placed at certain distance from each other. Okay, this is placed at certain distance from each other attracts each other with a force F. If 1/3 mass of one of the object is transferred to other object, what is the new force? Okay, now you can say this is my, let us take M, and this was my M. The separation was R. Now what is the force between them? G m1 m2, so m square divided by r square. What is the condition now? 1/3 of the mass of one object is transferred to other. So I'll transfer, let us take this mass, 1/3 of this to other. So what will be the remaining mass? Remaining mass will be 2/3. Okay, 1/3 is transferred. So remaining is 2/3 here. So I'll say this is my 2/3m. And this will become m plus m/3. What is that? 4m/3. So this is my 4m/3. The separation is the same, r. Okay. These are point masses. I am showing it a bigger circle so that you can visualize that. Okay, these are point masses only. So when I say here force F dash, what it will be? G into m1. m1 is 2m/3. m2 is 4m/3 divided by r square. And what it is now? This is 8/9 gm square by r square. What is this? This is my f. So this becomes my 8/9f. So my f dash becomes 8/9f. What is that? Option C. Just a formula based question. Such simple questions are also asked in mains. Yes. Now, when I am discussing these questions, when I am solving these questions, although this video is recorded, but I want you to actively participate in this. If you are just saying, watching this video, you will get to know how things are being solved by the teacher or like that. But when you solve with me parallelly, you will understand things in a much better way. Okay, so make sure when you are solving, you actively participate on this. Solve the question parallelly and put your comments also. Okay, let us read it. Two identical particles, each of mass m, go around in a circle of radius r. Under the action of their mutual gravitational attraction, the angular speed of each particle is. Okay, so what is happening here is two particles are there. Let us take m1, m2. Okay, identical particle. Okay, m. So this is m. This is m. Due to mutual gravitational force, they are moving in a circle. So certainly these two particles will be diametrically opposite. Is there any doubt in this? No. Okay. Now here we see what will be the force on this? F, that will be g m square divided by the separation square. Let us take here radius is r. So this separation between the two masses is 2r. And they are moving in a circle of radius r. This is my r. From here to here, this radius is r. So on this mass, if I say this force F, what is this? F is equals to mass. These are moving in circle. So mass m into centripetal acceleration. What is centripetal acceleration? V square by r or omega square r. So let us put omega square r. Why so? Because I need omega. Now what is F? Put F. F will be g m1 into m2 is also m square. Okay. Divided by separation between them. What is that? 2r square, and this is m omega square r. From here 1m got cancelled and omega comes out to be what it will be? G into m divided by this 2 square will become 4 r square, 1r from here, r cube, root of this. So root of gm by 4r cube, and here radius was not r, radius was a, so it will become 4a cube. What is that? Option C. They are moving in a circle. So multiple times these type of questions are asked, like three particles are there on the sides of equilateral triangle. They are moving in a circle due to mutual gravitational force, or there are four particles on the sides of a square. They are moving, and identical particles. Okay, they are moving in a circle. So these type of questions are very much asked in mains. Very much, I am saying. Like that particular question is 4 times asked. 4 identical particle on the corner of a square. Okay, now let us discuss about the principle of superposition. Now, principle of superposition we discussed every time when there are like in charges also we discuss multiple charges are there, we need to find force on one of the charge, we use that. So what superposition tells is, let us take there are multiple masses, you want to find force on one of the mass. What you need to do? First write the individual forces due to each mass, take the vector resultant, that is the resultant force on that particular mass. So superposition principles is telling that the force on, you can say, a mass due to other is independent of presence of other masses. When you are writing force on one mass due to another mass, that is independent of the presence of other masses. Okay. Similarly, one by one you will write all the forces and take the resultant of that, that will become my total force. What I am saying is, let us take, here is my mass m1. Let me take different colors. Here is my mass m1. Okay. Here is my mass m2. Here is m3. Let us take, here is m4. And there is a mass m0. I want to find force on m0. So what I will do, individually I will write the forces due to each mass. When I am writing force due to m1, that force due to m1 is independent of presence of 2, 3 or 4. So due to m1, I will say this force will be in this direction, and let us take this as my f1, and what will be the f1? G m1 m0 divided by the separation square. Let us take this separation is r1, so r1 square. Similarly, I'll write f2 like this, f2, okay, f3, f4, and when I need to write the resultant force, I'll take the vector resultant of these forces. To take the vector resultant, we have multiple ways. Either you write each force in I cap j cap form, then take the resultant, or just here you can use like simplify, take the components, cancel few of the components, then take the resultant. That way also you can do, or you may use even triangular law if the three forces are there like that. Okay, so when I say the force, resultant force, that will be the vector sum of each individual force. Vector sum of each individual force. That point should be clear. It's not a scalar sum, it's a vector sum. Force is a vector, it's not a scalar. Yeah, so you need to consider the direction. Sometimes it happens, students do some silly mistakes, like multiple masses are there, need to find the force, add the magnitude. Okay, let us solve this question. We are having three identical masses, identical particles A, B and C of mass 100 kg. Each are placed in a straight line with AB is equals to BC is equals to 13 meter. Okay, let us show them. Take a dotted line. So, this is a circle. I need a straight line. Yeah. Three masses A, B and C. A, B and C each of 100 kg. Okay. So this is my A. This is, let us take B. And this is C. Each is 100 kg. And AB is equals to 13 meter. And BC is also 13 meter. Okay, now let us read further. The gravitational force on fourth particle P of the same mass is F when placed at a distance 13 meter from particle B on the perpendicular bisector of line AC. So perpendicular bisector line. Okay, this is the perpendicular bisector line. And I'm putting this, the fourth particle, let us take that as my particle P. Okay, they are giving P, and this distance is 13 meter. The value of F will approximately be, what is F? Yeah, the gravitational force on the fourth particle. On the fourth particle, this, okay, that is F. The mass is the same. So what we will do? We'll write force due to A, show the force due to C, show the force due to B, take the vector resultant of the three, that will be my resultant force. Okay, so when I write due to A, so this one, let us take this as my F1, okay. How much is this angle? This is 13, this is 13, so this is 45. Due to C, due to B, so due to B, this is F2. Due to C, this is my F3. How much is this angle? Again 45 degree. Now F1 and F3 are equal in magnitude. How? Because this side is 13 root 2, this is 13 root 2. So F1 and F3 are equal in magnitude. So the resultant of the two will be along the vertical and that will add with F2. Okay, so when I will say F total force here, my F, what is that? Let us take F1, F3, they are equal. So F1 into cos of 45 plus F3 cos of 45. So F1 cos of 45 plus F3 cos of 45 plus F2. F1, F3 we know. I can write this as single term only as my 2F1 cos 45 plus F2. Now here I was able to see that the resultant will come along the vertical. Therefore, I took the component of F1 and F3 along the vertical, add with F2. Getting it? These two were equal in magnitude. Therefore, I was able to say that the resultant will come along the vertical. If F1 and F3 would not be equal, I will not be writing it like this. If let us take F1 and F3 are different, then what? If they are different, I'll be taking the horizontal component as well. Okay, and then I'll be taking resultant with that. Okay, so what is F1? F1 is G into, let us take mass of each particle is m, so m square divided by r square. What is this r? This is 13 root 2. Okay, this is 13 root 2 square, so this will become 2 into 13 square into cos of 45, that is 1 by root 2 plus F2. What is this F2? F2 is this force. How much is that? That is G into m square divided by the distance, that is 13. So 13 square. Like that. So from here G m square by 13 square we will take common out. This 2 is getting cancelled. So this is 1 by root 2 plus 1. What is 1 by root 2? Nearly 0.7. So 0.7 plus 1 is 1.7. 1 by root 2 is 0.7 plus 1 is 1.7. So 1.7 into this is G m square divided by 13 square is 169. 1.7 into 100. We need to find approximately. Okay, so I am seeing approximately how much will be the answer. So I can cancel it like this. This is 100 here. M is also 100. So 100 will get cancelled here and this will become 100G. 100G. What is that? Option B. Getting it? You need to be a bit smart while doing the calculations. If you go otherwise, putting the value of root 2 1.4 here and then try to calculate 1.1 divided by 1.414 plus 1 and then putting the values and then try to calculate exactly, it will take way longer time. See here, they are saying approximately. When they are saying approximately and come to the options, even if, let us take, even if it is not mentioned approximately, first of all what I'll do, I'll come to the options, I'll see, oh, options are like, there is so much gap between the options. So I can do the calculations by taking some approximation. This I used to do, like in many of the questions when calculations are there, we have to be smart. First of all, come to the options. If the options are very near, you need to spend time exactly to find the exact answer. Okay, you need to find that, spend time to find the exact answer because the options are very close. If the options are very far, then what you can do? You need less time. You can do some approximation. You can cancel 1.6 with 1.7 and all that and get to the approximate answer and then quickly mark that, move ahead. So these kind of tricks you need to use in the exam. Okay, so 4 masses here we are having, move in a circle. This particular question is 4 times asked in mains. Again we are discussing this, the speed of each particle. So one of the particle we will analyze. I'll find the total force on one of the particle and that force I'll put as my mass into the centripetal acceleration. Okay, so let us take, I'm finding force on this particular mass. So due to This m, if I write the force, that will be in this direction. How much is that? G into m square divided by, what is this distance? This is r, this is r. How much is this distance? This is r root 2, because this is 90 degree, okay. R, this will be r root 2. So gm square divided by r root 2 square. So what will be that? 2r square. Similarly, force on this direction, gm square divided by 2r square. This is due to this mass. Now due to this mass also I need to find, that will be in this direction along the diagonal, not diagonal, along the diameter. So along the diameter or the diagonal also of the square, we can say. So how much is that? That is gm square divided by, how much is this distance? 2r. 2r square is 4r square. Now I need to take the resultant of this. If you see, the resultant of this force will be coming along the diameter only, or along this diagonal only, isn't it? Why so? Because the two components of these two forces along this will add, perpendicular components will cancel. So what I'll do, I'll take this component of gm square by 2r square along this. How much is this angle? 45. Similarly, this component along that. This is also 45. So 2 gm square by 2r square cos 45. The resultant of these two will be 2 gm square by 2r square cos 45. Getting it? Plus this. How much is this? Gm square by 4r square. Plus gm square by 4r square, and this is my total force. This total force on this particle is equal to mass into centripetal acceleration. Mass is m and centripetal acceleration we can write as v square by r, because I need to find v, therefore I wrote it like this. Is this clear? From here, m by r we can cancel. This 2 is getting cancelled. So this will become gm by r 1 by 4 plus 1 by root 2. This is 1 by 4, this is 1 by root 2, and this is v square, root of this. This becomes my speed. Let us come to the options. What is that? Okay, I can take 1 by 4 common out. Okay, it will become 1 plus 2 root 2 inside. 1 plus 2 root 2. 1 by 4, when it will come out, it will become 1 by 2 outside the root. So 1 plus 2 root 2. Yeah, option C is the correct answer. Getting it? So these type of questions are asked. Like in 2026, one question may be asked, like a triangle is there, 3 masses on the corner of this equilateral triangle, identical masses, they are moving in a circle due to mutual gravitational force. Find the speed. There what you need to do, take one of the particle, find the total force, write that force as mv square by r, from there you will get v. Instead of speed, time period may be asked. Okay, different varieties can be possible. Now gravitational field. What is gravitational field? If I ask you, two masses are there, this is my mass m1, this is my mass m2. Okay, now m1 and m2 are applying force on each other. m1 is pulling m2, m2 is pulling m1. Okay, they are applying force on each other. Is there any contact between them? No. How that force is applied? If there is no contact, how it is possible to apply the force? Like if I need to apply force, let us take I have to push a block. I need to touch that block. I cannot push the block directly. No, that is not possible. Okay, so here how the force is being applied? There is presence of field between them. The gravitational field of m2 is applying force on m1. Gravitational field of m1 is applying force on m2. Getting it? So there is presence of field. These forces are field forces. Okay, gravitational force is a field force. Okay, it's not a contact force. Gravitational force don't need a contact to apply. Okay, so there is a field. So if I say this is mass m, okay, at a distance r, if I take point P, I want to find what is the gravitational field at point P due to this mass. What is that? So what I'll do, this is my distance r. So what I'll do, I'll put a small test mass here. Let us take small m naught. Test mass I'll put. On that test mass, force will be in this direction, and I'll say this force as how much? Gmm by r square, okay, by r square, and the direction is minus of f. This is my r vector. I'll say this is minus r cap, like this. This is the force. I'm writing that in vector form. Now this is the force that is being applied on this test mass. Okay, so I'll say the gravitational field is force per unit mass. So divide this test mass m naught. This was m naught. So this becomes my gravitational field. How much is this? Minus gm by r square r cap. If you talk about the magnitude, I'll say just gm by r square. Minus sign means the gravitational field is towards the mass. Getting it? If there is a mass, I need to find the gravitational field. How much is the field? Gm by r square. What is the direction towards the mass? Therefore, there is a negative sign. Is that clear? Okay. And this test mass, when we are taking, we took this test mass to be very small, such that due to this test mass, m is not displaced. My r is not changing. Okay. So I took this very small, and this is how I got my gravitational field value of gravitational field at that particular point. Getting it? Okay. So similar to electric field. So electric field also we used to denote with E. Sometimes gravitational field is denoted with I also. Okay. So in many of the books you'll find I is used like this for gravitational field. Okay. So this is gm by r square. Now the point is, due to one point mass at a distance r, I am able to tell that my gravitational field there will be gm by r square. What if there are multiple masses? Then what we need to use? Again, use the principle of superposition there for field also. Okay. So for multiple masses, if I talk about, if I say field due to multiple point masses. So what we will use? We will use again principle of superposition. What is that? If there are multiple masses, let us take this is my m1, this is m2, this is m3, this is m4, and there is a point P here. I need to find the gravitational field. I'll find due to m1, that will be in this direction, E1, due to m2, that will be in this direction, E2, due to m3, due to m4. Okay, so the resultant field there will be the vector resultant of E1, E2, E3 and E4. This is what you need to do. So just like force. Now if at a particular point you know that the field there is E, if I put a mass there, how much will be the force? E into F, simple. Okay, so if you know at a particular point the field is E, at a particular point the gravitational field is E, and if I need to find the gravitational force, I'll say my gravitational force will be the mass that I'm putting there, m, into the gravitational field there, E. Simple. Getting it? You need not know what is the source of gravitational field there. No, If the gravitational field is given there, I need to find force on a point mass which I am keeping there. So I'll just say M into the field there, E. Getting it? Okay. Yeah. So let us do a question on this. Let us take equilateral triangle. Okay. Equilateral one. Solid. Yeah. This is my equilateral triangle. I'm having three identical masses. Let us take this is M, two identical masses first. This is M and this is a point P. This is point P and the question is find the gravitational field at P. Simple question. Side is given to you L, L and this is also L. Now do this. So what you need to do is take a pause, solve this question, then come back. I hope you are back. Okay. So when I'm finding gravitational field at this point, what I'll do, I'll find due to M and due to this M and then I'll take the resultant. So due to this M, the field will be in this direction. Let us take, this is my E. And due to this M, the field will be in this direction. Magnitude will be same. So this will also be E. What is E? If I say E, E is equals to G into M divided by the distance, that is L square. Two vectors are there at an angle 60 degree. What will be the resultant? 2E cos of 30. The resultant will be along the bisector. So take the component along the bisector, E cos 30, E cos 30. Getting it? What I am saying is, I know the resultant will come along the bisector. And this is my 30 degree. This is my 30 degree. Okay. So this field is E. Take that component along the bisector, E cos 30. This is E. Take the component along the bisector, E cos 30. So the resultant will be 2E cos of 30. Okay. So I'll say E net is equals to 2E cos of 30. Cos 30 is root 3 by 2. So this is root 3E. And this becomes root 3 into G into M divided by L square. There can be some multiple masses kept on the corner of a rectangle and then you may need to find the resultant field at the center or maybe at a particular point. Okay, so different cases can be there. Now let us discuss about gravitational field due to continuous mass distribution. Now continuous mass distribution can be, let us take a rod. Okay, you can say a rod is there whose length is given, mass is given and we need to find field at a particular point, or we may have a ring, on the axis of the ring we need to find, or we may have a disk, on the axis of the disk we need to find, or we may have an arc or a semicircular ring, on the center of that we need to find, or we may have a hollow sphere, or we may have a solid sphere. The same shapes we have considered in electric field case also, and the same things we are doing here. So many of the derivations, not many of the derivations, all the derivations are exactly the same. Okay, so if you have understood the derivations there, it will be a quick revision for you, or if you have not understood those derivations, you can understand them here, and when you'll revisit that particular chapter, you'll understand how the things are working. Okay, so first of all, let us take a uniform rod. Okay, so I'm taking a first uniform rod. Okay, so this is dotted. I need a solid one, and I hope this is fine. Yeah, this is a uniform rod and the mass is M. Okay, length is L I need to find gravitational field at a point that is, I'll say, at a point, let us take here P, and this distance is given from this end, and let us take this distance to be A. Now we need to find the gravitational field at point P. So how we will find? So till now I know how to find gravitational field due to one point mass. So what I will do, I'll make this rod, this is rod, okay, this rod is made up of several point masses. So one of the point mass I'll take, find the field due to that, another point mass, find the field due to that, another point mass, find the field due to that, and same way add that to find the resultant field. This is when I'm doing summation, this is a continuous summation that will be, and continuous summation means integration. So what I need to do? I need to do integration. So let us take at a distance from at a distance x from here. At a distance x from here, I'm taking a thin section of this rod, and this thickness is dx. Due to this dx, what will be the field there? That will be in this direction, and let us write that as dE. So if I write dE, this dx thickness, it is like a point mass there, okay. So due to that point mass, when I write my dE, so I'll say dE is equals to G into the mass of this small section. Let us take that as dm. So dm divided by the distance square. How much is that? X. So divided by x square. Is this clear? Now I need to put dm. What is dm? I need to put it. So dm I can say will be, here mass is distributed in the length. So I will say dm will be mass per unit length into the length of this dm part. Okay, length of this. What is that length? Dx. So mass per unit length is m by L into the length, that is dx. So put it here. So this will become G m by L x square dx. Integrate it. This was my dE. It goes from 0 to E, and I need to consider the total length of this rod. Now those who don't understand how to put the limits, they will put 0 to L. Answer will be wrong. Here you see my x is going from A to A plus L. I need to consider the complete rod. Okay, I need to consider the complete rod. I'm taking the x distance from this point P. So to consider the complete rod, x will go from A to A plus L. So the limit will be A to A plus L. Like this. Okay. Now put it. So E will become G m by L. This is my constant, I took it out. 1 by x square integration is minus 1 by x. Now put the limits. So G m by L, this I'll say this will become 1 by A minus 1 by A plus L. Taking the LCM, it will become L in the numerator. A plus L minus A will become L just, and that L will get cancelled with the outer L. So this will become Gm divided by A into A plus L. Okay, so this will be my total field at this particular point P. So whenever there is a shape which is not a point mass, if you need to find the field there, you need to do integration. Okay, now such question can come. This is a uniform rod. What if the rod is not uniform? Then the mass per unit length will be given in the question. You need to use that to find. We'll do a question asked in means. Generally, the standard shapes, if I talk about, for sphere, for shell, or let us take for a ring, all those standard things that we will do. For those results you can remember. This you need not remember. You can just quickly derive these type of things. This is not required. Now let us go move to the next shape, and let us take that to be let us take what we can take. We can take a ring, semicircular ring, because if we take complete ring at center, field will be 0. Let us take a semicircular ring. Yeah, so I'm considering a semicircular ring. Semicircular uniform ring. I know the results. In electric field, we used to have the electric field at the center of the semicircular ring will used to be 2k lambda by r. Same will come here. Instead, there we have constant k, that is 1 by 4 pi epsilon naught. Here we have constant g. So when I say 2k lambda by r, 2k lambda, this was the formula in electric field. Okay, so if I need to write the same formula in gravitation, how will I write? Instead of this k, which is my 1 by 4 epsilon naught, 4 pi epsilon naught, I need to use the constant that is here. What is that constant? That is g. So instead of k, it will be my g. So 2 g into lambda is, here this is charge per unit length, here it will be mass per unit length. Okay, so I'm taking that to be lambda only by r. I know the direct answer, but let us do the derivation. I'm considering a semicircular arc. Okay, we don't have an arc option. Okay, I'm considering a semicircular arc, or sorry, semicircular ring like this. Okay, this is the center, the radius is r. I need to, the mass is given as m and radius is r. We need to find the field at center. So what I'll do, first of all, let's draw, this is my x-axis. So what I'm doing, at an angle theta from here, I'll take one of the section, okay, small section. At an angle theta, I'll take a section of this ring which is making an angle d theta at the center. This is how we do. This is my theta, and the angle subtended by this small section there, this is my d theta. Due to this d theta section, there will be gravitational field here that will be in this direction, and let us take this is my dE. Okay, so how much will be dE? We will say dE is equals to g dm divided by the distance square. Distance is r, so r square. First of all, I need to write dm also. Here mass is distributed in the length. So what will be dm? Dm will be mass per unit length, m, divided by total length. What is that total length? Pi r. Mass per unit length into the length. How much is the length of this arc? It is subtending an angle d theta, radius is r. How much that length will be? R d theta. This length will be r d theta. Put the length r d theta. So this will become m by pi d theta. This is my dm. Okay, put this dm here. So this will become g by r square, and this is m by pi d theta. This is my dE. Now, conceptual thing. Listen it carefully. From symmetricity, I can say the resultant E will be in the upward direction. Why so? Will there be any horizontal component? No. Horizontal component will be 0. Why so? If I am taking this d theta here, same small section you can take on the other side, the horizontal components will cancel, the vertical component will add. So resultant, when I'll find resultant, that will come along the vertical direction. So what I can do, I can just take the vertical component of this and integrate. So my total E will be integration of the vertical component just. What is vertical component? This is dE, horizontal is dE cos theta, vertical is dE sin theta. So this is dE sin theta. Now this will become gm by pi r square. okay, into sine theta d theta integration. Limit will go from theta is equals to 0 to 180 degree. I need to consider the complete ring. Theta will go from 0 to 180 degree. Getting it? 0 to 180 degree. What is integration of sine theta minus cos theta? This will become 2. So this is 2gm by pi r square. M by pi r is my lambda. So this is 2g lambda by r. Same formula, 2k lambda by r, isn't it? Yeah. So you can relate the formulas of electric field formulas and gravitational field formulas. I know due to a charged semicircular ring, that is 2k lambda by r. So here it should be 2g lambda by r, and we did the derivation, we got it as it is. There is no difference. Do you need to remember this? Yes, you can remember it, because you need this formula in both the chapters, here also, in electric field also. Now let us consider, let us find gravitational field on the axis of a ring. Okay, let us do that. So field on the axis of a uniform ring. Okay, so I am having a uniform ring. Let us draw that. Oh, not this shape, this shape. Okay, with solid line. Yeah. And let us draw the axis also. Okay. So consider this, that this is my ring, and this ring is placed in YZ plane. Okay, and I want to find the gravitational field along the x-axis at a point P. At a point P, I want to find the electric field. This point P is on the x-axis. The radius is r. So the same derivation that we did for electric field also. So we will take one of the small section here. Its mass is dm. Due to this small section, if I write the gravitational field there, that will be along this line, and that will be, let us take this is my dE. Okay, and I know that the resultant of all the components will be along x-axis only, because anyways the vertical will get cancelled when you will consider the similar point mass on the other side. So what I will do, I will just take the horizontal component and integrate that. Okay, so if this angle is theta, so when I say E is equals to integration of dE cos theta. What is dE? dE is equals to G into mass here, that is dm, divided by distance. What is this? That is this distance. I am considering this to be x, this is r, so this distance is root of r square plus x square. Okay, so this distance square, it will become r square plus x square. Put it here. So this is integration of G dm divided by r square plus x square into cos of theta. What is cos theta here? In this right angle triangle, how much is cos theta? Base, that is x, divided by hypotenuse, that is root of r square plus x square. So that is x divided by root of r square plus x square. Put your cos theta here. So that is x divided by root of r square plus x square. I need to integrate it. Now, do we need to substitute dm also? No, that is not required. Why so? Everything else is constant. Only variable is dm. Everything else is constant. You see x is constant. Will x will change if you consider different point masses? No. Theta will change? No. They will remain the same. So everything else is constant other than dm. Everything else will come out. Integration of dm will be m. So it will become g into m divided by gm into x divided by r square plus x square to the power 3 by 2. Got it? Do you remember the formula for electric field also? Yes, that is kqx divided by r square plus x square to the power 3 by 2. There the constant was k, here the constant is m. There the charge we need to put q, here we need to put m, mass. Everything else is same, no change. You remember that formula? kqx divided by r square plus x square to the power 3 by 2, electric field on the axis of a uniformly charged ring. You need to remember that. If you don't remember, make sure you remember that. That is required. Okay. Now, can you find on the axis of the disk? Yes, you can find. You can consider the disk to be made up of so many rings. Okay. Due to each ring, you write there. Okay. And then you can integrate it. One of the ring you take, write the electric field there, integrate to find the total gravitational field. This formula is required. You can remember it. Now, let us do the same exercise that we did for hollow sphere. Okay, let us take a uniform hollow sphere. I am considering uniform hollow sphere. Uniform hollow sphere. Okay, let us draw a sphere with this color. Okay, not dotted. I don't need dotted one. Need solid. Okay. Now there can be two cases. Which two cases that we considered previously? Inside and outside. As you remember, if I take a point outside the sphere will behave like a point mass placed at its center. If I take point inside the sphere, the field is 0. You remember that uniformly charged hollow sphere, inside the electric field is 0, outside the electric field is kq by r square. You remember that formula? Yeah. Okay. So inside, if I talk about, the electric field is 0. Okay. So for r, which is less than r, first case, take any point at a distance r from the center which is less than r. There the electric field will be 0. Gravitational field here. Okay, so E is equals to 0. Second case, R greater than R. You are considering a point which is outside it. Let us take here. This is my point P and this is my distance R now. So what will be the field there? How we will write it? Consider this sphere of mass m, radius r, to be a point mass that is kept at the center. What will be the field? G into mass divided by the distance square. Got it? Same thing. So we can draw also here how my gravitational field is varying. This is my gravitational field. I'm just writing the magnitude, not with the direction. Okay, so I'm just writing the magnitude, how the magnitude is varying with distance r. So till r is equals to r, it is 0. It is 0 till r is equals to r. Okay, r is equals to r, it is 0. After that, it is 1 by r square relation. So it will go like this. Before that, it is 0. And how much is this? This is Gm divided by r square. The field at the surface of this sphere. Same relations. Now consider a solid. I'm considering a uniform solid sphere. Uniform solid sphere. Let us draw the shape. We are having this solid sphere, and I need to write the field for both the cases. Case when R is inside, the point is inside, and when the point is outside, both the cases. So outside is very easy. Outside is very easy. So if we talk about R greater than R, this is my point P. Okay. From the center, this distance is my R, which is greater than the radius. Here mass is M, radius is R. So this entire sphere will behave like a point mass which is kept at the center. So I write the field here, it will be G into M divided by R square. Okay. The first case is a bit different here when R is less than R. Less than R means my point is somewhat here. Let us take this is my point P, and here I will divide this sphere into two parts. Yeah, I divide this into two parts. One which is the outer shell, this. Now this point is inside this shell, the field due to shell will be 0. So this outer shell will not have any field there. Okay, this point is inside this shell. The field due to will be due to only due to this inner sphere, due to this. If this mass is m dash, this point is on the surface of this radius is r. So when I'll say the field there, I'll say it is G into m dash divided by r square. Point is on the surface. On the surface of a sphere, the field is gm by r square. Okay, now I need to put what is m dash. M dash. Now this is a uniform. This is a uniform solid sphere, means the mass per unit volume is constant. So when I say this mass m dash, that will be equal to my mass per unit volume into the volume of this. What is mass per unit volume? Total mass divided by total volume. Okay, this is mass per unit volume into the volume of this inner one. How much is this? 4 by 3 pi into small r cube. Here my 4 by 3 part is 4 by 3 pi part is getting cancelled, and what we are getting? So this is capital M into r cube divided by capital R cube. I got my m dash. Put it there. So E is equals to G by R square M R cube divided by capital R cube. So this will become Gm R by R cube. The same formulas we got for electric field also. Okay, if you remember that. Inside the solid sphere, the field was varying linearly proportional to R. Okay, and there the formula we wrote was KQR by R cube. Here it is GMR by R cube. Same thing. Now if I draw the relation, let us draw the relation. This is my R. This is my field. Okay, just the magnitude of that. Okay, so till R is equals to R, it is varying linearly. Varying linearly means different color. Let us take a different color, yellow. So till R is equals to R, it is varying like this. because it is proportional to r, increasing with r. After that, it is 1 by, okay, here I did a mistake. It should be small r square here. Getting it? I did a mistake there. The distance from the center we need to take, okay? So not the radius, from the center we need to take, that is gm by r square. Okay, after that the relation is 1 by r square, so it will go like this. How much is this? This is at the surface, which is gm by r square. I hope previously when I wrote the formula, okay, I took small r only there. Is this clear? So these type of questions are asked. Which of the following shows the correct relation of the gravitational field as a function of distance from the center of a, let us take, hollow sphere or a solid sphere? This can be asked. Now coming to the questions part. Okay, this question: a solid sphere of radius r gravitationally attracts a particle that is at a distance 3r from its center with a force F. Now a spherical cavity of radius r by 2 is made in the sphere and the force become F2. What is the value of F1 is to F2? Now try to understand this. You can use superposition here. You can consider this to be a complete sphere having mass, having positive mass, plus a small sphere having negative mass. Okay, when you superpose that, you'll get it like this. Now negative mass, theoretical concept, that is, getting it? Okay. So solid sphere of radius r gravitationally attracts. Initially if I write this total distance is my 3r. So from here it is 2r. This is my r, radius of this. So I can say this distance is r from here till here. Radius is r, okay. So initially if I write F1, this was F1. So if I write F1, what will be F1? G into product of the masses mm divided by my distance from here square. This is my F1. Now I need to write F2. So when I say F2, how will I do? First, I'll find field there due to this and I'll multiply this mass with this mass m. The same thing I did here. When I was writing the force due to this complete solid sphere on this particle mass m, how I wrote that? I wrote the field first. How much is that? Gm divided by distance square. Why so? This point is outside the sphere. This sphere will behave like a point mass at the center. So Gm divided by the distance is 3r square into the mass. Field into the mass, that becomes my force. Getting it? Now this I'm finding F2 now. I'm considering this as made of this complete with positive mass, okay, positive mass plus this removed portion of negative mass. This complete of positive mass plus the removed portion, this portion of negative mass. So when you superpose that, you'll get this resultant shape. If I say this total shape, this positive mass is having mass m, what will be the mass of this negative mass? How much is the volume? Density we will consider to be the same. Okay. For complete, for radius r the mass is m, for radius r by 2 the mass will be m by 8, because volume into the density is constant, volume will become 1/8, volume become 1/8 means mass will become 1/8, so the mass of this is minus m by 8. So when I write field here, due to this complete solid, if I write the field that is in this direction, how much is that? G into m divided by 3r square. This is due to complete. Now due to this negative mass, so G into minus m by 8, so a negative sign will come, so minus G into m by 8 divided by the distance from the center here of that will become 2r plus r by 2, that is 5r by 2, so divided by 5r by 2 square. Okay, now let us take gm by r square common out here. Okay, yeah, let us take gm by r square common out here. Gm divided by r square common out here. Inside the bracket it will become 1 by 3 square, that is 1 by 9, minus this is 1 by 8, and then this is 5 by 2 square. 5 by 2 square will become 25 by 4. 25 by 4, okay, 4 into 2, so this will become 25 into 2 is 50. Like this. Okay, how much is it is now? This will become 41 divided by 9 into 50 into gm by r square. I need to find the ratio, therefore I am not multiplying that with 50. This becomes my F2. Okay, this is my field. I need to write the force, I'll multiply with small mass m there. So this becomes my F2. Okay, I need the ratio of F1 by F2, and that will become 50 by 41, that is option B. So use superposition. When some part is removed, consider that part to be of negative mass with complete portion having positive mass. So when you superpose that, it will become this portion as removed portion from the complete one. So it's the same thing, like I need to write the field at that point, I'll write due to complete portion minus the field due to this removed portion. Same thing, isn't it, in simpler words? Okay, another question. Let us read it out. A metal wire of uniform mass density having length L, mass m is bent into form of a semicircular arc. Any particle of mass m is placed at the center of the arc. The gravitational force. We know the formula of gravitational field on the center of the arc. Okay, multiply that with mass. That will become your gravitational force. Just do it. Pause the video. Solve it. Then comment your answer. Then come back. Okay, I hope you are doing that and you are back now. Okay, I am insisting one thing, that is just watching video is not sufficient. When you are watching this video, you should have a notebook and a pen with you, and when I am saying just pause this video, you should pause this video and then just try to solve it. Even if it is not possible, no problem. When you will try to solve the questions, then only eventually you will solve the questions. If you are not trying only, you will see, sir, I am not getting the things. I will not be able to solve this. Just try it. Try. Okay. So somewhat you would have understood. Okay, like this we have to do. These things we have to do. You might not be getting everything. Sometimes it happens. Like let us take, there is a difficult topic for me, and I am trying to understand that difficult topic. And I'm initially made my mind, this topic is very difficult, and I'm very sure I will not be able to understand it. Okay, and I'm sitting in the class, seeing the teacher, discussing the concepts, solving the questions, and when he is saying you try this question, and I'm not trying also. So for sure I'll not be getting anything from that. But let us take that particular topic is very difficult for me. I know that is very difficult, and it's very difficult for me to solve the questions. But when teacher is saying things, I'm writing them down, I'm listening carefully, I'm getting the concepts, and I'm asking the questions as well. Okay, you can ask here, this is a recorded video, but at least you can put your questions in the comment. We'll come back and reply there. Okay, so I'm asking the questions, and when the teacher is saying solve these questions, I'm solving the question, and I'm solving the question parallelly as well. So it will boost your confidence slowly. Okay, I did this mistake. Oh, I need to avoid this mistake. If I would have avoided, my answer will be correct. At least that confidence will be there. Okay, then when next time similar type of question will come, then you know, oh, I know this, how to do this. I did this, and I did that mistake that time, but this time I'll make it correct. So slowly the confidence builds up. It's not that all of a sudden and you putting like pen and notebook and solving the questions. No, that is not possible. That is not possible. Not all of a sudden it is possible. Slowly the confidence builds. Solve one question, maybe very simple. Got the confidence. Understood the concepts, move ahead. solve next question, understood the concept, then moving ahead, slowly building up the confidence, then you will be very confident after some time. Oh, gravitation, any question from gravitation I can solve, but this will take time. Getting it? Yeah. So when you are watching this video, so watch it carefully, understand the concept. I'm explaining things in a very simple way, very simple way. From the basics I'm going. Okay, so just try to understand what I'm saying and then do yourself also. Let us take, I'm doing derivation for a electric field. Do that parallelly. Or what you can do is just seeing my derivation, then pause this video, then try to derive yourself also. Derivation may not be asked in the exam. Like I'm deriving the electric field due to, let us take ring. That derivation may not be asked. But when you derive that, concepts will be built and you will remember that formula. Okay, 2k lambda by r here. Here that is 2g lambda by r. Same thing. So let us put that. So here the field is 2g lambda by r. This is my gravitational field into the mass m. Now I need to put the variables in terms of the variables that are given in the question. Uniform wire, mass having uniform mass density, length is L, mass is m. So what is length? L, I'll say that is my pi r. So r, when I'm saying r will be equals to L by pi. Okay, radius is L by pi. I need to put radius here because radius is not given. Okay, L by pi, and my lambda is mass per unit length, m by L. Put that. So 2g lambda is m by L by r is L by pi into m. So what it is now? 2g m pi by L square. Yeah. D option. Okay, I need not do derivation. I know the formula. I can do it quickly, which will save the time. Because ultimately, time is the currency in exam. Time is the currency. You can say like you need to understand how you can save time. If you understand how you can save time, you can get very good score. And if your concepts are, let us take, strong, and you have, let us take, a decent confidence also, and you have a decent practice also, but if you are not smart, you'll miss many things in the paper. In exam, like there in mains, previous year there was one question in mains and that was very lengthy. When I was solving that question, the paper came and then we were making solutions of that. So when I was solving that question, so it took me 7 to 10 minutes. That question was very lengthy. Very lengthy question. Now suppose if you do mistake of solving that question in the exam, that question was taking 7 to 10 minutes for me. For you it will take, you can say, 15 to 20 minutes and you may not get the answer as well. You may do some conceptual mistake because there was a point in that question where it is very easy to make a conceptual mistake. Okay, and I was going to make that as well. Okay, but I understood, okay, oh yeah, this is a mistake here, I corrected that. So in exam you have to be a bit smart. This question I'll avoid that question. Now if you avoid that one question, and with the same energy you can solve 4 questions, 5 questions with the same energy, and you'll be confident in those 4 or 5 questions because they were very easy. There are many questions which were very easy, many questions which were just straightforward, but if you stuck with those questions which are not at all worthy, like to invest your time and energy, and then you like although you know the things, but you'll miss many questions. You may say, sir, the exam was very easy, few of the questions were difficult, but I didn't get a very good score. Why so? I did these mistakes. These are, you can say, very like not what I should say. I'll say this, like you need to be smart. That this is the only thing I can say. You need to be smart in the exam by seeing, like, many times a question is having a very difficult diagram and you can see, oh, very difficult diagram is there, so many variables are there, although that question is conceptually very simple, but I know it will take a lot of time for me. Okay, so many data is there in the question. If I try to put the values, calculations only will take 10 minutes. So avoid that. Move ahead. There are questions which appears to be difficult, but they are very straightforward. Do them. Move ahead. Okay, like these type of question, this question, you quickly know like what is asking here. It is asked, what is asked here? Find the gravitational force. Okay, gravitational force I need to find here. So I can just, by seeing the diagram only, I can understand the question. Okay, need not even read everything. Reading is good, you should, there may be something else which may be asked, but here I can quickly like see, okay, I got it. Now what I need to do, I need to find the, I'll find the field due to this ring on the axis, multiply with the mass of this sphere. That will become my answer. Okay, let us do this. So due to this ring, if I write the gravitational field at this point, okay, what is that gravitational field? E, that will be K, not K, I was saying for electric field, that is G, that was K Q X divided by R square by X square to the power 3 by 2. So G into M into X, that is root 8 R divided by R square, radius is R, plus X square, root 8 R square, it will become 8 R square, whole to the power 3 by 2. This is my field. How much is this? This will become root 8 by, this is 9 to the power 3 by 2, that is 27, root 8 by 27, root 8 by 27 into Gm by R square. This was small m. This was my ring. This was small m. So put this as small m. Okay, I got the field, multiply with this mass m. So my force will be root 8 by 27 Gm m by R square. Come to the options. Root 8 by 27. Okay. Like these type of questions, very quickly we can do. I'll show you one question also which was very lengthy here. We'll come to that. Now here the mass density of a planet of radius r varies with the distance r from its center, as this is how the density is varying. The gravitational field is maximum at where the gravitational field will be maximum. Now we need to write gravitational field as a function of distance r first, and then we'll see at what particular value of r that expression will be maximum. Certainly that will be inside only, or critically maybe on the surface, because if you talk about outside, if you are outside, when you move away the gravitational field decreases because total mass is at the center. Outside it will keep on decreasing. So that point will be somewhat inside or on the surface, it may be. Okay, because here distances, the distribution is not uniform. If the distribution is uniform, then the gravitational field will be maximum at surface. This is non-uniform, so we don't know how what will be the value of r. For that we need to do integration here to find expression of the field first. So let us take this is my sphere. Okay, let us find the field at a distance x or a distance r. I am finding field here. So for that, what I will do, I will divide this into two portions, the inside one and the outside one. The field due to this outer portion will be 0. I need to consider only the field due to this portion. If the mass of this portion is m dash, I will say the field there will be g m dash by r square. This we know. Now the point is finding m dash. That is a difficult task, not a difficult task. That is what we need to make efforts for. Okay, so I need to find m dash, mass of this. So what I will do, I will consider this sphere to be made up of so many shells. I will take one of the shell at a distance, let us take x from here. At a distance x from here, I am considering this shell, and the thickness of this shell is dx. So if I write the mass of this particular shell, that is my dm, dm will be the density there, that is rho, into the volume of this shell. How much will be the volume of this shell? 4 pi r square is the surface, 4 pi x square, the radius is x. Oh, 4 pi x square is the surface area into the thickness dx. So 4 pi x square dx. Okay. Now density is varying. Here this is a function of r, I can put it as a function of x. So this will become rho into 1 minus x square by r square. Okay, this is my rho as a function of x. So it will become my rho into 1 minus x square by r square, x square by r square into 4 pi x square dx. This I need to integrate, and this will become my 0 to m dash, this will become my m dash. This is what we need to do. Now simplify it. 4 pi rho I'll take out. 4 pi rho. This is x square will go inside, and x square integration will be x cube by 3 minus, for the second term it will become x to the power 4, and that integration will be x to the power 5 by I'm writing properly. Oh yeah, this will be x by x to the power 4 only. Yeah, so that will become x to the power 5 by 5. So x to the power 5 divided by 5 into r square. This becomes my m dash. Put it there. So my electric field will become, let us write this with different color. So the electric field here will become 4 pi rho g, okay, g into 4 pi rho, yeah, x goes from 0 to r, yeah, limit was 0 to r, limit I forgot to put, this was 0 to r, so this will become r cube by 3 minus r to the power 5 by 5 r square. So put it there. So by r square, and inside it will be r to the power 3 by 3 minus r to the power 5 by 5 r square. Expression is right. I hope there is no calculation mistake. Okay, put it there, put it here, then we'll see how to get the maximum value of this. So this will become 4 pi, let me write here what it is now, 4 pi rho g, inside the brackets it is r by 3 minus r cube by 5 r square. Okay, this is electric field. Where it will maximum? I don't know. Do dE by dr is equals to 0. So if you put that, so this differentiation it will become 1 by 3 minus 3 r square by 5 r square, this is equals to 0, and from here I got my, yeah, I got my r as 5 r square by 9 root of this, that is yeah, r square if you take out it will become just r, so this is root of 5 by 9 r. A bit lengthy question. Okay, getting it? Now you may say, sir, you just did differentiation one time, do we need to do second time differentiation to check whether it is maxima or minima? No, one time differentiation is enough, because the at center I know that will be 0 minimum, okay, and yeah, at center it is 0, the minima is at the center, the field will be 0 there. Okay, so what we will get will be maxima only. Now here this question to find the field due to yeah, a rod, so here we need to find the field due to rod, and this is a non-uniform, here the mass per unit length is given to you. So here lambda will not be constant. Let us read it out. A straight rod of length L extends from x is equals to a to L plus a. The gravitational force it exerts on a point mass m at x is equals to 0. So we'll find field at x is equals to 0, then we'll multiply this with that point mass. This is the rod. This is my origin, okay, O. And this rod is going from x is equals to a plus L. Here is my point mass. So first I'll find field there and then I'll integrate that field to find the total field, multiply that with point mass. This is what I'm going to do. So I need total field due to this rod at center. So what I'll do, at a distance x from here, I'll take a small section of this rod of thickness dx. Due to that thickness, I'll write the field here. That is my dE. So if I write dE will be equals to G into dm. Dm is the mass of this thickness dx divided by the distance square, x square. What is dm? Dm is mass of this small section having thickness dx. So I'll say that it will be mass per unit length into the length. Length is dx. So this is g into lambda into dx divided by x square. What is lambda? Lambda is this. This is by lambda. Put it here. So this is g by x square into lambda is a plus bx square into dx. This I need to integrate to find the total field. Okay, and then I'll multiply with mass m to get the answer. I'm not solving it fully, I'm leaving it for you. Now here, pause this video, solve this question, comment your answer, and then you need to come back. Okay, just do it quickly. Okay, I hope many of you are doing it. So what it will become? So this g, when I integrate the first term, this is a by x square. So this will be a by minus a by x it will become, okay. 1 by x square integration is minus 1 by x. And for the second term, it will become b into x. Okay, x square is getting cancelled, only b. So that will become bx. And x goes from a to a plus L. So now you can put and force, so multiply this with m. Put the limits, you'll get the answer. Okay. Now acceleration due to gravity. Acceleration due to gravity we use in kinematics chapter for projectile motion. We discussed that g, small g, that is equal to 9.8 and sometimes we take 10. But that g is, the value of g 9.8 is on the surface of earth. If you move away from the surface of the earth, that will decrease. As you are moving away, you know earth is a solid sphere. Okay, earth is a solid sphere. Okay, as you moving away from the center of the solid sphere, if you move away, what will happen? The field will decrease. Okay, so this g will keep on decreasing, isn't it? The force will be lesser, g will keep on decreasing. So this g is actually near the surface of earth only, that we take. But yes, because we know that radius of earth is 6400 kilometer. So if we take up to even few kilometers, we can take approximately g to be 9.8 itself. But if we are moving to, let us take 1000 kilometer, 2000 kilometer or multiples of r, then we need to consider the different values of g. For projectile motion, you are throwing a ball at 20 meter per second, 50 meter per second, it will not go up to that height. We know that. So there we can consider g to be constant, and that is perfectly correct. There is no, you can say, mistake in that. So first of all, we are discussing here on the surface of earth. Okay, so this is my earth, radius is r, mass is m. consider point mass near the surface of Earth. So how much will be the force on that? Let us take this mass is small m. So you'll say the force on this, that is towards the center F, will be G m m by the distance square. So if you write the acceleration, that is force by mass, that will become G into m by r square. This becomes, and this is my acceleration due to gravity, small g. So small g comes out to be gm by r square. Keep this thing in mind. If you put the value of small g, if you put the value of this universal gravitational constant, the mass of the Earth, the radius square, this value comes out to be nearly 9.8 meter per second square. Okay. Now it may be asked in exam, find the acceleration due to gravity on the surface of that planet whose mass is like this, whose radius is like this. So if for another planet you need to find, you put the mass for another planet and put the radius for another planet, like that. I can write this this expression in terms of density also. Let us write that. G mass, I can write density into the volume divided by r square, you see. So this will become 4 by 3 pi into rho g into r. This becomes my g in terms of density. Okay, we have some variations of questions on this. Many questions are asked from acceleration, variation of acceleration also, and acceleration on the surface also. Variation of acceleration, variation of g with height and with depth and with omega, those also. We will come to that part later. So first let us do questions on this. The acceleration due to gravity on surface of Earth is g if the diameter of Earth reduces to half of its original value. Half of original value means radius is getting half. Mass remains constant. The acceleration due to gravity on the surface of Earth would become. So g we know, that is gm by r square. This we know, that is clear to us on the surface of Earth. Now g dash, he is saying mass remains as it is, but the diameter become half, means the radius will become half. So in place of r, you put r by 2. So what it will be? 4 gm by r square, and this becomes 4 times of g. 4 times of g, that is D option. Okay. Yeah. Another question. A planet has double the mass of Earth. Its average density is equal to that of Earth. An object is weighing W on Earth. Okay, will weigh on that planet. How much it will weigh on that planet in terms of W? So first of all, W we know, that is mg. Okay, and I can write g as gm by r square. So W is gmm by r square. This we know, that is clear. Now this another planet is having double the mass of Earth. The density is same. The radius is not given. So can we find the radius? Yes. Density is the same. Density for Earth is mass of Earth divided by volume. Density of that planet that is having double the mass of Earth. Radius I don't know, so let us take small r, the density. So from here the radius small r. So from here 4 by 3 pi is getting cancelled and m is getting cancelled. So the radius of that planet comes out to be 2 to the power 1 by 3 times the radius of Earth. I got it? So W dash, when I will say, that will be g mass of the object. Mass of the planet is twice. So 2m divided by the radius of that planet square. So 2 to the power 1 by 3 square is 2 to the power 2 by 3 divided by r square. How much is this? 2 divided by 2 to the power 2 by 3 is 2 to the power 1 by 3. So 2 to the power 1 by 3 into g small m into capital M divided by r square. And how much is this? this is my W. So this is 2 to the power 1 by 3 W. 2 to the power 1 by 3 W. C option. Is this point clear to you? Easy questions are there, not much difficult. Great. The questions are not that difficult from gravitation topic. Another question, the radii of two planets A and B are R and this is 4R, it should be R. Okay, and their densities are rho and rho by 3. The ratio of acceleration due to gravity and their surfaces, okay, at their surfaces, that is GA by GB will be. So let us write G in terms of density. So G is GM by R square. Let us put mass in terms of density. So that is density into the volume. So this is basically 4 by 3 pi rho G into R. 4 by 3 pi rho G into R. So I can say G is proportional to density into radius. Everything else is constant. Okay. So when I say GA by GB, that will be rho A into RA divided by rho B into RB. Simple. What is rho A by rho B? So first of all, what is rho A by rho B? Rho A is rho and then rho B is rho by 3. So this will become rho divided by rho by 3. So that is 3. Then what is RA by RB? R and 4R. So R divided by 4R by 4. So this becomes 3 by 4. C option. Okay, this question was asked in 2023. Such simple questions are asked in mains. Therefore, I am saying that many of the questions are just simple and straightforward in the exam. And these type of questions are there in the exam. When you come out of the exam, then you see, oh, these questions were simple, I missed them. Why so? I was stuck by the difficult question. I was stuck at the difficult question. So those mistakes you might have committed before if you appeared, and you might have committed during the mock exams also. So don't repeat those things in the exam, because when you come back and you'll see, oh, these 3-4 questions were very, very simple and I missed them. That will be the greatest mistake. Okay. And actually these type of things decides the rank. Just knowing the concepts is not enough. You have to prove yourself in the exam. Okay, variation of acceleration due to gravity, first due to height. Okay, first you can say variation due to height, and then we'll consider the depth, and then we'll consider at a particular angle. Okay, so at a height. So let us take, this is our Earth, and at a point P, which is having a distance r from the center of Earth and height h from the surface of Earth, if I write the force on this mass, I am taking a mass there, m, how much that will be? You'll see that force F, that will be towards the center, will be G into mass of Earth into mass of the object divided by the distance square. In terms of height, if I write this formula, okay, let us write first acceleration. Acceleration will be F by m. That is my acceleration. I am taking this acceleration as G dash. So G dash is basically G into m divided by my r square. If I write this formula in terms of height, so this will become G m divided by r plus h square. If I take r common from here, so this will become G m by r square into 1 plus h by r square. if I write gm by r square as my acceleration due to gravity on the surface of Earth, so this g dash will become g divided by 1 plus h by r square. I got the expression. Okay, at a height h, I can write acceleration due to gravity like this. Now, let us take an assumption that this h is very, very small. Let us take that assumption. So, if h is very, very small, then what we will do? This I can write as g dash as g into 1 plus h by r to the power minus 2, 1 plus x to the power n. Okay, when x is very, very small with respect to 1, so that will become 1 plus nx. Okay, so I'll take just the first term of the binomial expansion. So this will become g into, higher order terms we are neglecting, 1 minus 2h by r. Keep this thing in mind that this formula is only applicable when h is less than r. Less than r means h is r by 100 at least. Okay, we say 100 times or 50 times it should be. So h should be 1 by 100 of h. If h is less than that, or 1 by 50 of r, not h, h is less than r by 100. If this assumption is there, we can consider this. Okay, we can consider this assumption if this condition is there in the question. Sometimes this condition is given, that consider the h to be very small, then find the value of g there. Okay, getting it? We got it? Now next thing, with depth. Second, let us consider at a depth how g will vary with depth. We are going inside the Earth surface. This is our Earth. You are considering a point. Let us take here P, which is inside this Earth. You made a tunnel. Okay, so I need to find, let us take this is, I made a tunnel and I am putting the point mass m there, point mass m there, and I want to find how much will be the force in this case. So this is like a solid sphere condition. Okay, so I'll say the force there will be my field into this mass. What is the field there? G m into the distance from the surface, from the center, that is r. So gm r divided by r cube into this mass m. This becomes my force. Okay, just divide this with m and you'll get acceleration. So acceleration g dash f by m, that will become g into m r divided by r cube. Okay, and r you can put in terms of depth. So this depth from here, this I am considering as my depth d. So put r as, r is the distance from the center, so that will be my total radius r minus this r, so that will become my d. So g dash is coming out to be g m by r cube into r minus t. Keep this expression in mind, and to remember it, like you can take a solid sphere, you know the field at a certain distance inside the solid sphere, that is gm by gmr by r cube, and put r is equals to r minus d. That's all. Next, due to rotation of Earth. Okay, I'm writing here the third condition. Rotation of Earth about its axis. Generally, when we say G, so we don't take the rotation effect. So we may say that that is the acceleration due to gravity at the poles. Okay, because at poles, if you talk about, the rotation effect will not come. On the equator, the rotation effect will be maximum. Okay, so let us consider that rotation effect now. So let us take this is our Earth, and let us draw the axis of the Earth as well. This is the axis of the Earth, and it is rotating with angular velocity omega, like this. Now, a point if you consider at a certain angle theta here, at a certain angle theta, I am putting my mass m. Now let us find the total force on this mass m. Now Earth is rotating. So in rotating from, if you observe this mass m, there will be a what? Pseudo force outside. What is that? Centrifugal force. So one force, that is force due to gravity, this is m into g. Okay. Another force will be pseudo force, and that is away from the axis like this. And how much is that? M into the acceleration omega square r. Okay, omega square into r. What is this? That is this r. How much is that? R cos of theta. This is my r cos theta. The radius is r cos theta. So into r is r cos of theta. Now to find the resultant force due to Earth, I need to take the resultant of these two, mg and m omega square r cos theta. These two. This angle is theta. So if I take the total along the axis, it will become mg minus this component along the axis m omega square r cos theta into cos of theta, because this is also theta. So this will become cos square theta minus m omega square r cos theta into cos theta, so cos square theta. This is component along the axis, and perpendicular to the axis will be m omega square r cos theta into sin theta. Okay, and these two will be perpendicular. To find the resultant, L square. Root of this. This becomes my total force. Are you able to understand how I am writing this equation? First, along the axis, how much is the total force? Mg minus m omega square r cos theta into cos theta. This is the along the axis. The perpendicular component will be m omega square r cos theta into sin theta. That is the perpendicular. So these two are perpendicular. So to find the resultant magnitude, root and square that. Okay. Now, if you talk about this second term, this is very, very small. Okay, so this second term is very, very small, so we can neglect that in front of this first term, and this f nearly comes out to be mg minus m omega square r cos square theta. And if you want to find the acceleration, divide this with mass m. So this becomes my g dash. Considering the rotation effect, this becomes my g minus omega square r cos square theta. So you need to remember this. Okay. Okay, now moving to the questions part, there are so many questions asked from this particular section in main. So many questions. Variation of acceleration due to gravity. So many questions are there. Okay, so let us do some of the varieties of the questions asked. At what distance above and below the surface of Earth a body will have same weight? Okay, above and below. What distance above and below? So this is Earth, not a dotted one, needs solid. So this is Earth. So he is saying same distance above and same distance below. So let us take a distance d above and a distance d below. Okay, let us take, this is my point A, this is my point B, and I need to say GA is equals to GB. Okay. Also, one more thing I need to tell you there when I was discussing variations. So here you can draw that curve also, the variation of G with respect to the distance from the center of the Earth, that curve that may be asked in mains. So variation of G with respect to the distance. So G dash I'm saying. So till radius of Earth from the center, G will be increasing linearly. Okay, G will be increasing linearly. At surface it will be maximum, that is 9.8. After that the relation will be 1 by r square. It's just of the solid sphere. The same relation we did for solid sphere, it's the same thing. This is my 9.8 meter per second square. Now coming back to our question. Okay, now if I write GA, how much that will be? GM divided by r square. R is radius of Earth plus d. So r plus h square, or you can say r plus here d square, like this. This is equal to, at distance b, now this becomes my r minus d. This is the distance from the center. So this is gm into r. R is r minus d divided by r cube. Okay, GA, GB I wrote, equated them. Now solve it. So GM is getting cancelled. Yeah, and what I can do, r cube is equal to, take this other side, r plus d and r minus d, it will become r square minus d square. 1 r plus d will remain. Multiply it, it will become r cube minus rd square plus dr square plus not plus, minus d cube. R cube, yeah, perfect. R cube, then plus rd square. Oh, I did a mistake, I think. Okay, I'm multiplying first r. Okay, so r cube minus rd square. Okay, then r square d, yeah, and then minus d cube. Yeah, perfect. This is r cube, this r cube is getting cancelled. So this becomes a quadratic equation in d. We need to find d, by the way. Okay, so let us write it, taking whole on the left. So this will become r d square. Yeah, this is a, okay. There is a cube also. So what I will do, first I will take d common out of this, and then that d will become 0 on the other side when it will go. So this will become r d minus r square plus d square, this is equals to 0. I am taking d common first from here, and then whole I am taking on the other side. Therefore this become r d minus r square plus d square. Okay, this is a quadratic equation in terms of d. Yeah, Getting it? Now you can use the expression like this is a quadratic equation. I need to write the solution for this. So minus b plus minus root of b square minus 4ac divided by 2a. Okay. So minus b. So minus r plus minus root of b square minus 4ac. So plus 4r square divided by 2a. So that is divided by 2. So I need to consider plus sign only because negative is not possible. So this will become root 5 minus 1 into r by 2. That is option D. Yeah. Okay. Now in this question, it was not mentioned that this D is very, very small. Therefore, when I cannot take that assumption G dash at a height dash to be G into 1 minus 2h by r. That assumption I cannot take here. Okay. Yeah. Another question. Assuming the earth to be a sphere of uniform mass density, the weight of a body at depth r by 2 from surface of earth, if its weight on the surface of earth is 200 Newton. Now at a depth r by 2, what will be my G dash? G m r minus d divided by r cube. Now when I was writing this formula, I converted that in terms of G also, or I left that as it is. Okay, I can convert this in terms of G also. So G dash is equals to this G into 1 minus d by r. Okay, in terms of G, you can write it like this. Any of the way you may remember, like which one is easier for you to remember, you can remember. I generally write directly like this because I relate that with solid sphere. Therefore, I write like that. But if you want to remember in terms of G, you can remember in terms of G as well. No problem. Yeah. So this is G into 1 minus d by r. I need to take another step like this. Okay. So what is G? G I'll put as it is. 1 minus what is D? D is r by 2. So r by 2 by r is 1 by 2. So this becomes G by 2. So G dash is half of G. So weight will become half of 200. Initially it was 200. It should be 100 now. Okay. Initially it was 200. Therefore it will become 100 now. Easy question. Very simple question. And this was asked in 2023. You see, when I see very simple questions asked in mains, I feel like students should not miss this thing. Like any student should not miss that thing. If he missed that thing, it means that's not good for him. Easy questions are must to do questions. So whenever you have like you go in the exam center and you are seeing. So first of all, identify the easy questions. Okay. So identify the easy questions and quickly solve them quickly, and then come to moderate questions, and then come to difficult questions. That is the key, which I like always used to do. What I used to do in the exam. So in our time, the paper was used to be offline. So in 2013, the paper was offline. So January it was. So I got the question paper sitting in the exam hall. First of all, the chemistry section I used to pick because I know that I can like finish chemistry in 20-30 minutes, maximum 30 minutes, minimum 20 minutes. In chemistry, I know something, it's okay. I don't know something, I leave it. Okay. So I'll solve quickly, solve the chemistry. If there are some questions which require calculations, I will leave them. Which requires a bit more calculations, I'll leave them. And then go to physics, solve the questions. Okay, most of the questions I know, like if the 30 questions used to be there. Okay, so if 30 questions are there, now it's 25. So let us take you are there. So 25 questions are there. So out of them, out of 25, you will be able to solve 20. Okay, and if you are, let us take few of the questions are like a bit difficult, then you may do at least let us take you did 18 questions as of now. So you did 18 questions out of 25, then you move to maths. You did easy question there as well. Now you are coming back. Now you are coming back, and you know, like in physics, I left few of the questions which were moderate and which needs time. Then coming back, doing those questions, okay, and then few difficult questions will be there, leave them, then move to chemistry, attempt the remaining question, then move to the math, attempt the remaining question, and then let us take last 15-20 minutes are there, or last half an hour is there. Then you go to pick few of the difficult questions, and that also you have to do smartly. Now there are difficult questions of the topics which are difficult and of the topics which are easy. If a question which is very difficult but of a topic which is easy, I'll attempt that first. Why so? Because I know that topic which I am not confident with, I may commit some error. Anyway, the question is difficult. Okay. So if a question is there which is of easy topic, but question is difficult, it requires some calculation, I can do calculation. Okay, I have 15-20 minutes, at least 2 questions I'll do from these. Okay, so do them. These 2 questions will decide. Okay, these will be decided. Like I did all the easy questions. Okay, so I'm above average. Then I did the moderate level questions, I got a decent rank. Now I did the very difficult questions, few of the very difficult questions, I got a good rank. This is what you need to do. Okay. If the angular velocity of Earth's spin is increased such that the bodies at the equator start floating, the duration of day would approximately be. Okay, bodies at Earth's equator start floating. It means G becomes 0, isn't it? The mass is here. So one is force due to gravity, that is mg. In rotating frame, we have a centrifugal force outside. This is m omega square r. My G effective, my effective force, if I say the resultant force F, this is mg minus m omega square r. And start floating means this becomes 0. It means omega square r becomes equal to G, and omega becomes root of G by r. And if you write the time period 2 pi root r by G, okay, and this will come out to be approximately 84 minutes. This expression 2 pi root r by G, seen many times, many places. It will come to this in oscillations also. If a tunnel is there, that is along the diameter or along the chord, okay, the time period of oscillation, that comes out to be this 2 pi root r by G. Okay. Another question. The acceleration due to gravity on the Earth's surface at the poles is G, and angular velocity of Earth about its axis passing through the pole is omega. Okay. An object is weighed at the equator at a height h above the poles by using a spring balance at a height above the pole at a height h here. By using a spring balance, okay, if the weights are found to be same, then h's, okay, and the equator and a height above. So at equator here and at this point, the weight comes out to be same. It means G is same at both the places. This assumption is given to us, so we will use that. So let us take this is A, this is B. So I'll say GA is equals to GB. What is GA? This assumption if I take, I can write this as G into 1 minus 2h by r. What is GB? GB is G minus omega square r. Simple. Okay. So G will get cancelled here and we'll get 2hgr, yeah, not r, by r, 2hg by r. This is my omega square r, and from here my h comes out to be omega square r square by 2g, omega square r square by 2g, A option. Is this clear? I got this assumption. This assumption was there, therefore I took the formula with assumption 1 minus 2h by r. Otherwise, if this assumption would not be there, I will not be considering this. I will not be writing it. I will be writing g divided by 1 plus h by r square, like that. If you don't remember, let me come back to show you again. I am saying that this formula is with assumption. This is the general formula. Then that assumption thing was given there, therefore I considered that. Now, gravitational potential energy. So, gravitational potential energy we discussed in work energy power also, and we discussed that if a mass m which is at a height above the surface, we write their potential energy considering surface to be reference as mgh. Okay, considering g to be constant. But here we will be considering distance which are far more than or comparable to the radius of r. So then we need to consider g to be variable. There we cannot consider g to be constant. Also, here our reference will be different. Now there we considered the surface to be reference. Here we will consider reference to be different. Anyways, reference is not going to change anything. But we consider the reference here to be infinity. There we consider the reference at the surface. Okay, two difference you got. There g was constant. Here g is variable because the distance is too large. Okay, there my reference was surface. Here my reference is at infinity. Okay, so two masses m, another mass small m are there. I need to find how much is the potential energy. So the potential energy will be the work I will do to put these two masses at a distance r. The work I will do to put these two masses at a distance r, that will be the potential energy of these, isn't it? So how will I put? Initially, I'll consider that they were a long distance away. Okay, that they were at a long distance away, and I was bringing my small mass m slowly from infinity. I was bringing this small mass m very slowly. Very slowly means with constant speed or negligible speed. Okay, so at any instant, let us take this point mass is somewhat here at a distance r. I am bringing it slowly. Now when I am bringing it slowly means it is coming with nearly constant speed. Okay, so constant speed means zero acceleration. Zero acceleration means I will be applying equal and opposite force as that of gravity. What is the direction of force due to gravity? Towards this. This is my force due to gravity, and how much is that? That is g m by r square at this instant. I will be applying equal and opposite force F, then only I will be moving it slowly, isn't it? So if I say this is my force F, so magnitude of F will be gmm by r square only. I am bringing it slowly. The amount of work I will do, how much is that? Work done will be integration of F dot dr, that will be integration of, magnitude is same, gmm by r square dr, limit initially it was infinity, finally let us take it as at a distance r, so this will become gm m minus 1 by r, limit from infinity to r, so this will become minus gm m by r. I got my work. This work I did. This is a negative work. Yes, I did negative work. I was moving it in this direction. I was applying force in that direction. You got it? Like the mass was moving in this direction, I was applying force in that direction. Work done should be negative only. Yeah, I got that as negative. Now this work, where it will be stored? In potential energy. So I'll say my change in potential energy will be equal to my work done. This is work done by the external force. So final potential energy minus the potential energy at infinity is equals to minus Gm m by r, and I considered my potential energy infinity as my reference. This is, I'm considering 0, considering this as reference. So I got the potential energy at a distance r as u is equals to minus G m by r. Remember this formula? If you ask me how much is the work done by the gravitational field, opposite of this. Opposite of this. Gravitational field did work GMM by R. I discussed when conservative forces are there. Okay. So work done by the conservative force is equal to negative of change in potential energy. Work done by external force is equal to change in potential energy when the particle is moving slowly. Getting it? So keep this thing in mind. Okay, so if two masses are 2 point masses are there at a distance r, how much is the potential energy? G minus Gmm by r. Okay. Now, if you have multiple masses, okay, let us write potential energy of multiple point masses. Two masses are at a distance r, potential energy is minus Gmm by r. If multiple masses are there, then what? Let us take, this is m1, this is m2, this is m3, this is m4. So when I write the potential energy, you need to write the potential energy of all the pairs. For each pair, I need to consider the potential energy. Okay. Also, you need to understand one thing, that potential energy is a scalar. What is the unit? Energy. This unit is joule. Okay. So potential energy is a scalar. Potential energy is a scalar. So I can just add all the magnitudes. So when I'll write the total potential energy of this system, what I'll say? I'll say this is sum of all the potential energy of each pair. For each pair. How many pairs are there? Let us take here when I'll make the pair. So this is potential energy of 1, 2 plus 4 masses are there. How many pairs will be? 4C2. 4 into 3 by 2, that is 6 pairs. 1, 2, 3, 4, 5, 6. Okay, like 1, 2, 3, 4 and then 5, 6 like that. So when you say I'm 1, 2, 2, 3, 3, 4, 4, 1, 1, 3, 2, 4 like that. Take potential energy of each pair and just add that. That will become the potential energy of my system there. Same thing here. We are having 5 masses. Okay. 4 spheres, each of mass m, form a square of side d. A fifth mass, capital M, is situated at the center of square. Okay. The total gravitational potential energy of the system is, what is the gravitational potential energy of this whole system? For each pair I need to write. Okay. So first of all, forget this. Let us write the potential energy of these 4 masses system. So 1 pair, 2 pair, 3 pair, 4 pair. Okay, these are the 4, 2 diagonal one. So it will become minus 4 times of, let me write with different color. Yeah. So this will become minus 4 times of gm square divided by the distance between them, side is d, so d square. 2 diagonal, so minus 2 gm square by, oh, I did a mistake. What is that? This. It shouldn't be square, it's not a square. They just did just the distance. I did mistake previously also. No, everything is proper. Yeah, it's not a square distance, just the distance there. Okay, so divided by the diagonal distances d root 2. So d root 2. This is potential energy of these four. Now consider this additional. So this will have 4 pairs with each of these. Okay, so minus 4 times of g capital M small m divided by distances diagonal by root 2. Yeah, half of the diagonal. So d root 2 by 2, d by root 2. Everything is fine. Okay, what we need to take common? Gm by d. So let us take Gm by d as common out. So minus Gm by d, I am taking common inside. So with small m it will become root 2 plus 4. So 4 plus root 2. With capital M it will become 4 root 2. Now let us come to the expressions. Which option is correct? I think A option is correct. Yeah. So 4 plus root 2 into small m plus 4 root 2 into capital M. Yeah. Okay. Now let us talk about gravitational potential. So basically potential is potential energy per unit mass. As we discussed in electrostatics also, the potential was potential energy per unit charge. Here the potential is potential energy per unit mass. Okay, so when I say my potential at a point V, so I will say the potential energy at that point divided by mass. Okay, so what is the potential energy? I am considering here two masses. This was my mass m. This is another small mass m. They are placed at a distance r. Okay, I need to find potential at this point P. So the potential energy minus gmm by r divided by this mass m. So due to this capital M, I got the potential at a point. What is that? Minus gm by r. Not that r, small r. What is the unit of this? Joule per kg. Unit is joule per kg. The SI unit. This is not volt. By default, when we say potential, we think like electric potential only. Okay, that is volt. But this is gravitational potential. So this is joule per kg, not volt. Okay, so I got the formula. Due to a point mass, the potential at a point P at a distance r is minus gm by r. So this is due to one mass. What if there are multiple masses? What if there are multiple masses? Let us write that. Potential due to multiple masses, point masses. Okay, so let us take this is m1, this is m2, this is my m3, this is my m4, and I'm writing potential at a point P here. So when I write potential, because we know potential is a scalar, I need not consider direction. So I'll write potential due to each one. Okay, so when I say potential at P, so I'll say this is potential due to m1. What is that? Minus g into m1. What is the distance? Let us take that is r1. So r1 minus g m2 by r2 minus g m3 by r3 minus g m4 by r4. Just add that. Just add the magnitude. Okay, potential is a scalar. Need not worry about the direction. I'm considering here this distance as r1, this distance as r2, this as my r3, and this as my r4. Now let us try to derive the relation also between potential and the field, the gravitational potential and field. For electrostatics, we know the formula. E is equals to minus dV by dr. Okay, let us see, is the formula same here also? So when I say my potential is potential energy per unit mass, so I will say my change in potential is equals to my change in potential energy per unit mass. What is potential energy? Change in potential energy is negative of work done by the electrostatic force. Change in potential energy is negative of work done by the electrostatic force, not electrostatic force, gravitational force here. Sorry, by mistake I mentioned minus of work done by the gravitational force. Here we are considering gravitational force. So minus of work done by the gravitational force. Okay. Now, how much is the work done by gravitational force? What I did, I by mistake mentioned a negative sign there. Okay, let me write it again. I'm writing it again. I by mistake took a negative sign there. Okay, so my potential is change in potential energy per unit mass. What is change in potential energy? That is negative of work done by the electrostatic force. What is the work done? F dot dr. What is F? E into m dot dr divided by m. So from here I got my dv as minus E dot dr. So if you write E in terms of V, you can say E is equals to minus dV by dr, or you can say my V as, or yeah, V as, not V, let me write dV. My dV as minus, dV as minus of E dot dr and integrate it both sides. Like that also we can write. Okay, so any of the relation, like if we need to find electric field from potential, you can use this relation. If you need to find potential from electric field, you can use this relation. Okay, so here let us find potential due to multiple masses. Consider a question where we are having a square consider it to be a solid one. I'm having a square let us take this is mass m, this is mass 2m, this is mass m, and this is mass 2m, and this is the center of the square, and the square is having a side L. This is my point P, that is at the center of the square, and the question is find the potential at P, or center. Find the potential at center of the square. How will we do this? Due to each mass, we'll write the potential. So when I'm writing at center, due to this 2m, what I'll say? This is minus G into m is 2m divided by, what is this distance? L by root 2. L by root 2. Due to this m, so minus g m by L by root 2. Each is having the same distance. Due to this 2m minus g 2m by L by root 2. Due to this m minus g m by L by root 2. And this becomes my total potential at P. Potential at P. Okay. Is this clear? Potential is very simple because it is scalar. Just write individual potentials and add it. Now, gravitational potential due to continuous mass distribution. Now, consider there is continuous mass distribution. The same things you can consider we did for a rod, then we did for a ring, semicircular ring, then we did on the axis of a ring, then we did for a sphere, hollow sphere, then we did for a solid sphere. Let us do the same exercise for them. Now I am considering a uniform rod. Okay. So first case. Here we are assuming our reference at infinity by default. Whenever we are writing potential, we assume the reference to be at infinity. Zero potential is at infinity. That is by default, unless until it is mentioned. That will not be done. Okay. Anyways, so reference is by default at infinity. Again and again, I am not be saying that I am considering potential at infinity to be zero. No, that is by default understood. So due to uniform rod, I am saying let us take this is my uniform rod, and along the rod only I am considering a point that is at a distance. Let us take this is my point P here, and this distance is A, and the length of the rod is L. This is a uniform rod, mass is M and length is L. So you need to write the potential at P. How we will write? At a distance x, the same exercise I am doing again. At a distance x from here, I will consider a small mass having thickness dx. Due to this thickness, if I write potential there dV, that will be minus g dm divided by my distance x. What is my dm? Dm is mass per unit length divided by my length dx. Put it there, minus g by x m by l dx, integrate it. That will become my total potential. V is equals to minus gm by l ln x. The limit of x will go from a to a plus l. So here the potential will become minus gm by l into ln a plus l divided by a. Don't remember this expression, this is not required. Now let us consider, if I consider an arc, so all the total mass is at the same distance only. Okay, so it will be the same thing. So let us write that quickly. Due to a uniform semi-circular ring. So when I am saying semicircular ring, it is like this. We need to find potential at this point O. So if I write potential, each mass is at the same distance r only, so it will be just minus gm by r. Each point is at a distance r only. Now let us write potential due to a uniform ring, due to a uniform ring, on the axis of the ring. So due to a uniform ring on its axis. So you consider a uniform ring like this, not a dotted one. Draw the axis of this ring. Okay. I need to write potential at this point P. If you consider any mass there, small mass dm, this is scalar, so you know, take the components and all things. Okay, so if I write potential due to this there, dv will be minus g dm divided by the distance. Which distance? This distance. How much is this? This is x, the radius was r, so this is root of r square plus x square. Put this root of r square plus x square, integrate it. Everything else is constant other than dm. Integration of dm will become m, so v becomes minus gm divided by root of r square plus x square. Just a simple formula, need not even remember, it will be remembered automatically. You just do it once with me, you'll remember it automatically. That is not needed. Okay, due to uniform ring we did. Now let us do due to a hollow sphere. Yeah, due to a uniform shell. Shell means a hollow sphere. Same two things, two cases will be there. First, r less than r, second, r greater than r. If we talk about r greater than r, this whole mass will behave like a point mass which is kept at the center. So this is my point here. Whole mass will behave like a point mass which is kept at the center. Okay, mass is m here, radius is r. So if we write the potential, whole mass m will behave like a point mass here. So it will become just minus gm by r. If we talk about inside my gravitational field was 0. If gravitational field is 0, what is potential? Field is dv by dr, minus dv by dr. Field is 0 means potential is constant. Inside my potential is constant. Inside it is constant. On the surface, therefore, when I am moving out on the surface, it will be having the same value as that of inside. Okay, that's the boundary condition. And when you are moving out, the potential will decrease. The relation is given. So inside, the value of potential will be same as that of the surface. So V here will be just minus gm by r. Okay. And if you want to draw how V varies with distance r, you can show V need, inside it will remain constant, outside it will become minus 1 by r. Okay. Now let us draw that. Let us take a line. Potential is negative, so I am drawing on the negative side. So r, this is my potential, this is my V. Okay, so this is negative of that. So till r is equals to r, it is constant. After that it decreases in I'll say magnitude. Okay, so first initially it is constant. I will show it. We'll show it like this, minus gm by r. take a different color. Yeah, minus gm by r, and then it decreases like this. Okay, this is minus gm by r, and then this is 1 by r relation. This is r is equals to r. This is how the potential varies. After r is equals to r, this is 1 by r relation. So it goes like this. At infinity, it becomes 0. Okay, now let us do the same exercise for solid sphere. Uniform solid sphere. There, finding potential for that is a bit difficult task, as we did in electrostatic also. You see some lengthy expression there, kq divided by 2r square into 3r square minus r square. That expression, the same thing will be derived here. Okay, now let us write that potential due to a uniform solid sphere. Uniform solid sphere. So consider a sphere. Again, the two cases. Which two? R less than R. Second, R greater than R. R greater than R. If my point is outside, it will just like a point, behave like a point mass capped at its center. So I'll just write the potential as minus gm by r. That is straightforward. Now the challenge is with inside. Okay, so inside, let us take, I need to find potential at this point P. So one thing is we can find by using the relation between potential and field. We know that dV, what is that? dV is equals to minus E dot dr. This I know. Let us use this relation. So dV is equals to, what is E inside? That is gmr divided by r cube. This formula I derived. Field due to solid sphere, that is gm into r divided by r cube. What is the direction? Towards the center. dr is outside, out, like dr is in the direction of r. So dot with the dr. Okay, so its direction is towards, dr is out. So when you take the dot product there, a negative sign will come, so that it will become just minus, minus, it will become plus. Okay, so minus, minus, it will become plus. I'm just removing this minus. So it will become gm r divided by r cube dr integration. This is dv integration. What is the limit? I know the potential at surface, how much? Minus gm by r, because boundary condition. Okay, so outside the potential is varying like this. So put r is equals to r, the potential there will become minus gm by r. So at my and at a distance r, I don't know the potential. Okay, so distance I am saying that it varies from r to r. My potential varies from v to potential minus gm by r, minus gm by capital R. Okay, let us derive that. So dv integration will become v, putting the limits, it will become minus gm by r minus v, and this will be equal to gm by r cube. Integration of r is r square by 2. By 2 is there, putting the limits, so it will become capital R square minus small r square. Okay, so from here v comes out to be minus of gm divided by 2r cube into 3r square minus r square. And this expression we derived for electric charges also. There it was kq divided by 2r cube into 3r square minus r square. It was like this. Okay. And if I draw how it varies, how v is varying with distance, let us do that. This is my r minus of v, negative axis. Okay. So here I am having v. Okay. This is my r. So if you see the magnitude of the potential at is maximum at center, how much is that? Put r is equals to 0, that will become 3 by 2 times of the surface. And when you are moving away from the center, the potential keep on decreasing with one relation, this is this, and when you move out of the sphere, it will decrease like this. Okay, so this is my 3 by 2 times of the center, and this is my center potential. So it will go somewhat like this, and from center it becomes 1 by r kind of relation. It will go like this. Okay, how much is this? This is minus 3 by 2 gm divided by r, and what is this? This was my r is equals to r, and this is minus gm by r. This curve can be asked, therefore I am drawing these curve for the solid and hollow, both the cases. For field also I drew that. Now coming to questions part, having some of the questions. If V is the gravitational potential due to sphere of uniform density on its surface, then its value at the center will be, what is saying? Surface potential is minus gm by r, at center it is minus 3 by 2 gm by r. So therefore at center it will be 3 by 2 times of V. Getting it? Yeah, remember this relation. Another question. Gravitational potential at a point above the surface of earth is this, and acceleration due to gravity at that point is this. Assume the mean radius of the earth to be this, the height of that point is. So potential is given. So when I write potential, I'll say this is minus gm by r, above it is like this. Acceleration due to gravity, if I write g dash, what that will be? Gm divided by r square. That is this, isn't it? Yeah. Okay, because it is out, so distance from the center to be small r. Divide these two. So just take the magnitude, neglect the sign. So V by G dash, or you may consider the sign because anyway that sign will get cancelled. So V by G dash comes out to be R, isn't it? Minus R. Yeah. So I need the height of this point is, okay, first of all let us find R. So that is minus V by G dash. How much is minus V? So that will become 5.12 into 10 to the power 7 divided by, what is G dash? G dash is 6.4 meter per second square. 6.4. Okay, so how much is this? This is 51.2 if I do, divided by 6.4, this becomes 8, isn't it? Yeah, this is 8. Yeah, so this is so this is 0.8, so this comes out to be what is that? 8 into 10 to the power 4 is 8,000 into 10 to the power 3 becomes my kilometer, 8,000 kilometer. So what is height h? So height will be r minus the radius, isn't it? So 8,000 kilometer minus what is radius? 6,400 kilometer. This comes out to be 1,600 kilometer. 1,600 kilometer. Yeah. This clear? Now, if potential is given above the surface, from one data only I can find. From one data only I can find. Even G is given above the surface, from one data only I can find. But this relation, they give both of them. Why so? So that you need not do much calculation. You can just divide them and you'll get R directly. Getting it? Otherwise, this is extra data. I know this formula, here only I can find R and from there only I can get G. But for that I need to put the value of M and G both. So that will take time to do calculations. Okay, another question. A mass 50 kg is placed at center of a uniform spherical shell of mass 100 kg. So we are having a spherical shell and the mass of this is 100 kg. Okay. Mass 50 kg is placed at the center. So at the center we are having 50 kg mass. The radius is 50 meter. This radius is 50 meter. The gravitational potential at a point 25 meter from the center is, so we are having a point P here and this is 25 meter. What is Vp? So when I write potential, I'll write potential due to this 50 kg mass plus my potential due to this shell, both. Due to 50 kg mass, if I write, what is that? Minus G into M 50 divided by R, distance is 25. Due to this shell, this point is inside, the potential everywhere is same as that of the surface, minus Gm by R. So minus G into M is 100 divided by the radius, which is 50. So what it is? So this becomes minus 2G minus 2G. So this is minus 4G. Yeah, this is 2021. Now we have 5G. Okay. Acceleration, okay, relation between field and potential. We already derived that relation, so I am just writing the relation here. So my E is equals to minus of dV by dr, that we did. Okay, let me write it properly again. So my E is equals to minus dV by dr and my dV is equals to minus of E dot dr. I'm just writing the relation because we did the derivation for this previously. Now let us have some questions on this relation. Yeah, if the gravitational field in the space is given like this, taking the reference point to be at 2 centimeter. Now here reference is changed. I was saying generally it is not done and it will not be done, but in some questions if it is saying that we change the reference, then you need to consider the reference there. But also they are not considering it to be 0 here. Yeah, reference is at this and there the potential energy, they mentioned the potential to be 10. The gravitational potential at R is equals to 3 in SI unit. Okay, so what I have to find, I need to find V from R, E. So V is equal, dV is equals to minus of E dot dr. Okay, so write dV is equals to minus of that, so this will become just K by R square dr, limits. Potential is 10 when R is equals to 2 centimeter. I need to find potential V when R is equals to 3 centimeter. And one more thing, this K is given in joule centimeter per kg. Therefore, don't convert this centimeter to meter. The unit will get cancelled with K. K is in terms of centimeter only. Okay, so be careful. So when I solve this, it will become V minus 10. It is equals to, K is my constant. I'll take out minus 1 by R. It will go from 2 to 3. So this will become what? Everything is fine. Yeah. So this will become minus K. This will become 1 by 2 minus 1 by 3. Yeah. So minus is there. So 1 by 2 minus 1 by 3 is 1 by 6. So this becomes K by 6. K is 6. So this becomes 1. So V comes out to be 10 plus 1, which is 11. B. So here they change the reference and they consider that reference to be at 10 joule per kg. Now let us discuss about conservation of mechanical energy. We discussed conservation of mechanical energy in work energy power chapter. So again the same point I will say, if only conservative forces are acting, total mechanical energy will be conserved. Okay, so if a particle or a mass is moving under gravitational force only due to another planet, or let us take due to earth, you will say the total mechanical energy will be conserved. Okay, so what is the total mechanical energy? E is equals to kinetic plus my potential energy, and this is constant when only conservative forces are acting. So if only conservative forces are acting, I'll say my initial kinetic plus my initial potential is equals to my final kinetic plus my final potential. Total mechanical energy will remain conserved, it means that will remain constant. Some questions. Two planets having mass m and 16m and their radii are a and 2a respectively. Separation between the centers of the planet is 10a. Okay, so one is having radius as a, another is having 2a, this is a, this is 2a, their centers are at a distance 10a, so the distance between the centers, this is 10a. A body of mass m is fired from the surface of larger planet towards the smaller planet. So from here it is fired like this along the line joining the centers. For the body to be able to reach the surface of smaller planet, here it has to reach the minimum speed, minimum firing speed is, so this is velocity v. So what is the minimum value of v? Now you may say, from here we have to fire the this ball, or what is that, this body has to reach here. So just conserve the mechanical energy. Here kinetic plus potential, for minimum you can consider kinetic here 0 is equals to here kinetic plus potential, you get the value of v. No, that is wrong. Where why it is wrong is, try to understand. When you are throwing this mass m from here, from this point like this, when you are throwing it, so a point in between will come where the force due to smaller one will be greater than this bigger one. After a certain point, the force due to smaller one will be greater than the bigger one. So if this mass just reaches that point, it will automatically be attracted by the smaller one, isn't it? It just reaches the point where the force due to the smaller one is greater than this bigger one. Okay, this ball after that point it will just be attracted. So for minimum v, I'll say it critically reaches there. It means it reaches with 0 velocity at that point. Okay, so what is that point in between after which the force due to smaller mass is greater, or the smaller sphere is greater than the bigger sphere? Here I'll say that this is my E is equals to 0. E is equals to 0 means the field is 0 at that point. From here just you make this point pass this line. After this the field due to this will be greater, it will be automatically attracted. So where the field will be 0, let us make E is equals to 0 here. The field due to this sphere in this direction, that will be, I am considering this to be x. Okay, so minus g into m divided by, what is this is m, this is another is 16m, minus gm divided by x square is equal to minus, why I am considering minus, I need not consider the sign, I am just equating the magnitudes of the two to cancel. Total field is 0 here. So I am saying Gm divided by x square is equals to G into 16m divided by 10a minus x square. Gm got cancelled. 4x comes out to be 10a minus x. So x comes out to be 2a. X comes out to be 2a. So this is 2a and from here it is 8a. Now this is my initial condition. This is my final condition. This is my 2 here. I'm critically throwing it such that it just reaches this point. For V to be minimum, I'll consider the velocity at point 2 to be 0. Okay, I am applying now conservation of mechanical energy. So I'll say kinetic at 1 plus potential at 1 is equals to kinetic at 2 plus potential at 2. Kinetic at 1, I am considering that velocity to be V. So half mv square. What is potential at 1? When you write potential here, you need to write potential energy due to bigger sphere as well as due to smaller sphere. So due to bigger sphere, that is minus G into m is 16m divided by the radius 2a. Due to smaller sphere, that is minus G into m divided by the distance. What is the distance from here? That is 8a from the center of this, 8a. This is initial potential energy is equals to. For V to be minimum, final kinetic energy I am considering here to be 0. Potential final here due to smaller minus G into m divided by x is 2a minus G 16m divided by how much is this distance? 8a. This is the equation. From here we have to solve V. Okay. Let us solve. Half. I did a mistake here. I just wrote the potential. I need to write the potential energy. And when I'll write potential energy, I'll just multiply with small m. And anyway, that small m is going to cancel. So this getting cancelled. Okay. Now taking everything towards the right, we can simplify for V. So we write V is equals to. Okay, by 2 also I was cancelling. Yeah, let us cancel this properly. So this half, this will become 4 here. This will become 4 into 2. 4 into 4, yeah. Perfect. Now let us write it properly. So V is equals to, what's there first? Minus Gm by A, minus 4 Gm by A, that is minus 5 Gm by A. And here we are having 16 Gm by A. So it will go on the other side plus 16. So minus 5 plus 16 is plus 11. So just it will become plus 11 here. Plus 11 Gm by A. Simple. Let me write it again properly. This G is not looking good. Okay. So this is 11 Gm by A and this term plus Gm by 4A. So this is what? 11 into 4, 44 plus 1, 45 by 4 Gm by A. This is my V square. This was V square. Root of this is my V. So what it will become? This will become, okay, 9 into 5 is 45. 9 I'll take out. It will become 3 by 2 root 5 Gm by A. Getting it? Okay, this was a lengthy question and this was asked in mains 2020. And if this question appears in the exam, such type of lengthy questions, I will prefer to avoid at that time because it requires multiple steps and it is very easy to do some silly mistake during the exam writing the equations. So as of like when I'm attempting the paper in the first go, although this concept is easy, I will avoid this question, and at the end I will come back to this question to solve it there with peaceful mind, because I have completed the paper. Now I'm having full focus on this question. I'll be able to do it properly. Okay, escape speed. Now escape speed means with what minimum speed you should throw a particle or a mass such that it escapes the gravity. It will not come back. Now generally I throw a ball, it will come back. Again throw, it will come back. It means it's not escaping. But if let us take, I throw with a very high speed, it never come back. I'll say it escaped. Okay, so escape speed is the minimum velocity. Okay, minimum velocity needed for a particle to escape the gravitational pull of a planet. Generally, when we say escape speed, by default we consider it from the surface of the planet. Okay, so by default it is from the surface. Okay, so let us consider a planet solid line. Yeah, so let us consider a planet, and I am throwing a mass with velocity v from the surface. Okay, and now it escaped. It went to infinity. I need to find the minimum velocity. So when it is reaching to infinity, I am considering here v is equals to 0 critically, because I am finding here minimum velocity. Therefore, I am considering the final there the velocity is 0. Now, this is my point 1. This is my point 2. I am applying conservation of mechanical energy. Initially, the mechanical energy is, I am considering the mass of this point is m, mass of the planet is m, radius is r, capital M and capital R. Okay. So, initial potential energy plus initial kinetic energy is equals to final potential energy, which is 2, plus final kinetic energy is 2. This is U1 and K1. What is initial potential energy? From the surface it is minus gm by r, mm by r. What is the initial kinetic energy? Half m. This is my v escape square. This I am considering as my v escape. Okay, ve. Finally, potential energy is 0 because it is at infinity. If you write minus gm by r, r is infinity, that is 0. Also we consider reference to be at infinity, so therefore it is 0. Plus the kinetic at infinity, it is just critically reaching, so v is equals to 0 there. So from here we got my escape velocity to be root of 2 gm by r. And for Earth, if we put the radius of Earth and mass of Earth here, we get the answer to be 11.2 meter per second, kilometer per second, 11.2 for Earth if we do. Okay. Questions. Coming to the questions. Let us read. Escape velocity of a body from Earth is 11.2. If the radius of the planet to be 1/3 of the radius of Earth and mass be 1/6 of the radius of the Earth, the escape velocity from the planet is. Okay, mass is changing and my radius is changing, and accordingly we need to find escape speed. One more thing. This escape speed I wrote in terms of radius and mass. I can write in terms of density also. Okay, I can put mass as 4 by 3 pi r cube. So this will become root of 2 g. I will put mass as density rho into 4 by 3 pi r cube volume. So this becomes in terms of my density. Like sometimes the relation is with the density, therefore I am writing it. Do not remember specifically this formula, no, just put mass as 4 by 3 pi r cube into the density. Now coming back to this question. So if I write the formula, V escape is equals to root of 2 gm by r. Now for another planet, V dash is equals to 2g into mass of this planet is 1/6 that of Earth, m by 6, and radius of this planet is 1/3 of the Earth. So what it will become? 3 into 2. So this will become just gm by r, root of gm by r, yeah, which becomes 1 by root 2 times of my VE. So what is this? This is 11.2 divided by 1.414, or 1 by root 2 you can write nearly 0.7. So 11.2 into 0.7. So what is this? 11.2 and we are having 0.7. Let me multiply this first. 112 and 7. 7 into 1, 8, 7. 7, 8, 4. Okay. 11.2 into 0.7, it will become 7.84. Yeah, 7.84. 7.84 means 7.9. D option. Yeah. Getting it? Okay. Now another question. A rocket has to be launched from Earth in such a way that it never returns. If E is the minimum energy delivered by the rocket launcher, what should be the minimum energy that launcher should have if same rocket is to be launched from surface of the moon? Okay. It means I have to give such energy that it escapes. That much energy I have to give. Getting it? How much is that? Half mv escape square, or directly only you can say that that is equals to the initial energy, kinetic energy plus the potential energy becomes equal to 0, that is minus gmm by r. Okay, any one of the way you can say. So when I say E is equals to my gmm by r, this is the escape energy that is needed. Is that point clear? Yeah. So here it is saying if E is the minimum energy delivered by the rocket launcher, what should be the minimum energy that the launcher should have if the same rocket is launched from surface of moon? Assume the density of Earth and moon are equal, okay, and Earth's volume is 64 times the volume. If Earth's volume is 64 times, then Earth radius is this 4 into 4 into 4, yeah. So Earth's radius will be 4 times of the moon. It means radius of moon is equal to radius of Earth by 4, and density is same. Okay, I just need speed. Here it is asking for speed. No. Okay, these options were from previous question, I think. Yeah. So these options are incorrect by mistake. These options are of previous question. Anyways, we'll come to the answer. So this is the energy from Earth. This is for Earth. For moon, if I write E dash, mass of the moon, don't know. So mass of the moon, if I say the density is same, the radius is 1 by 4th, so the mass will be 1 by 64th. Okay, yeah. So G into m dash into m divided by r dash, I am saying. So G into m dash as m by 64 into m divided by radius of moon r dash as r by 4. So this comes out to be E by 16. Okay, so it will become 1 by 16th. Lesser energy, certainly less energy is required there. Okay, mass of the moon is 1 by 64th, radius of the moon is 1 by 4th, therefore we put that. Now let us talk about the another important section of this chapter, that is satellites. Okay. So let us consider this is our Earth and a satellite is moving around the Earth in a circular orbit. Which color? Let us take this. A satellite is moving around the Earth in a circular orbit like this. It is moving like this. This is in 3D. So if I draw in 2D, I may draw the top view also. So that will be easier for us to understand. Let us draw the top view. Okay. So this is my satellite here. Mass m. The radius of the satellite to be r. Mass of the Earth is m. The radius of Earth is r. Okay. And this satellite is moving in circle like this. So only Earth's gravitation is acting, that is the gravitational force. Now in space you may say, sir, so many objects are there, sun is also there. But generally when we consider, okay, one thing is they are very far, Earth is near, so we consider that gravitational only. But for our level we cannot consider that also. So on our level we consider due to Earth only. So due to Earth, this mass is m, it is moving in a circular orbit. So I'll say whatever gravitational force is there due to Earth F, this is equals to my mass into my centripetal acceleration, because this is moving in the circle. Centripetal acceleration v square by r. V square by r, it is moving with speed v. Clear? So what is F? F is g m divided by r square. This is my force, and this becomes equal to mv square divided by r. Small m, mass of the satellite is getting cancelled. It means what? The speed will be independent of the mass of the satellite. Yeah, this r is getting cancelled. So v comes out to be root of gm by r. You see, the speed of the satellite is independent of the mass of the satellite. It depends on the mass of the planet, but not on the mass of the satellite. And also, this r is the distance from the center. It depends on the orbit of the satellite, not on the radius of the planet. You may change the radius of the planet. If the mass remains the same, this will remain the same. Getting it? Yeah. So this becomes my speed. I can write this speed in terms of height from the surface as well. Gm divided by r plus h, if h is the height of the satellite from the surface. So I can write this in terms of h. Now let us write time period. So time period we know, that is 2 pi r by v. So 2 pi r by v is root gm by r. So in the numerator it will become r to the power 3 by 2. So we got the time period relation as 2 pi r to the power 3 by 2, and this relation is also important. And one of the most important thing to understand from here is t square is coming out to be proportional to r cube. When we will discuss Kepler's law, we'll come back to this. So time period square is proportional to cube of the radius. As radius increases, the time period will increase. As radius increases, the speed will decrease. Okay, getting it? Now let us talk about, and few of the other things if you have to find from here. Let us take omega. You have to find omega, you can write v by r, okay, or frequency you have to find, you can find from here. Okay, getting it? And let us take, you have to find the angular momentum of the satellite, that will become mvr. So all those things you can find. Angular momentum, if you have to write, let us take L, that is just mv into r, and v is root of gm by r. So angular momentum also you can write like this. So m root gmr You not remember this expression, I'm just writing it. Don't remember for angular momentum, no. Just remember this velocity. This is very important, most important I'll say. From velocity you can write time period also, but better to remember this as well because this is also important. Time period. Okay. Now energy of satellite. Now this satellite is moving in circular orbit. We got the speed of the satellite. If I write the kinetic energy of this satellite, you will say kinetic energy is always half mv square. This is the formula for kinetic energy. So half m into square of root gm by r. So what is this? This is gm m by 2r. This becomes my kinetic energy. And if I ask you what is the potential energy, you'll say potential energy is minus g m by r. What is the total energy of the satellite? Total energy is kinetic energy plus the potential energy, and if you find it, it comes out to be minus g m by 2r. Okay, just put the value k and u, you'll get it. Now the ratio of kinetic is to potential is to total. This ratio, keep this in mind, this is very important. Kinetic is to potential is to the total energy. If you see the ratio, this is 1 is to minus 2 is to minus 1. So 1 is to minus 2 is to minus 1. This ratio is important to remember. Multiple times it is asked and it can be asked again. So kinetic energy to potential energy to the total energy of the satellite ratio is this, and the formulas for kinetic energy and potential energy and total energy is this. Now if you see the total energy of the satellite is negative, what does it mean? It means the satellite is bound to the planet. The satellite is not free, the energy is negative. If you want to free that satellite, you need to give that particular energy such that the total energy becomes 0, it goes to the infinity. Minimum energy I am talking about, and that minimum energy we call that as the binding energy of satellite. Okay. Binding energy of satellite. So minimum energy to be given to the satellite for it to escape. Okay. So minimum energy needed for satellite to escape the gravitational pull, escape the planet, or I'll say. Okay, and how much is that? The total is negative, you give the same amount of that, that will become 0, it means it can escape to the infinity. So I'll say this binding energy is equals to g m by 2r. Just the opposite of this. Opposite means a plus sign of that. Okay, same, because some negative is, let us take minus 5 is there, you want to free, you need to give plus 5 to that, isn't it? Then it will be freed. Let us take you are having a loan of 10,000 rupees and somebody want to make you free from that loan. It means he has to give 10,000 to you, then only you will get. So your balance was minus 10,000, he gave 10,000, now you are free. Okay, it's like that. Okay, now let us come to some questions of satellites. Correct formula for height of satellite from Earth's surface is, okay, and it is, this formula is having time period. So let us relate time period with height. Now time period we know t is equals to 2 pi r to the power 3 by 2 by root gm. This formula we derived. I will write r as r plus h. R is distance from center. If I want to write in terms of height, it will become r plus h. Let us square the whole term first. So this is t square is equals to 4 pi square by gm into r plus h. From here I can write h. So from here if I write h, this comes out to be, okay, this was cube. this cube will come, yeah. So from here if I write h, this will become T square Gm by 4 pi square whole to the power 1 by 3 minus r. Okay, T square, one more thing, our answers are having small g in terms of Gm. So Gm by, I will multiply and divide with r square. So r square here and r square here. Now this Gm by r square will become my small g. So this will become r square T square g by 4 pi square whole to the power 1 by 3 minus r. R square T square g by 4 pi square whole to the power 1 by 3 minus r. I hope this is correct. Yeah. Don't remember this. You may say, sir, should we remember this result? No. Quickly you can write, like some variations can be there. The same thing he is asking, but you just need to arrange the variables properly. Another question. The orbital angular momentum of a satellite is L when it is revolving in circular orbit of height h from surface. Okay. So when I say L is equals to mvr. If the distance of the satellite from Earth's center is increased by 8 times to its initial value, the new angular momentum will be. So I need angular momentum in terms of r. So this is v, I can put here root of Gm by r. So this is m root Gmr. So my angular momentum is proportional to root of r. The orbital angular momentum of a satellite is L when it is revolving in a circular orbit at height h. If the distance of the satellite from the center is increased by 8 times, it is increased by 8 times. Initially it was r, now it is r plus 8r, means it becomes 9r. So L dash will be root 9r, proportional to that. So from here if I write L dash, that comes out to be 3 times of L. Okay, 3 times of L, D option. Another question. The mass density of a spherical galaxy varies as k by r over a large distance r from its center. In that region, a small star is in a circular orbit of radius r. Then the period of revolution t depends on r as. Okay. So mass density of spherical galaxy is k by r. So rho is given as k by r. This is something different. Okay. Over a large distance r from its center. In the region, a small star is circulating an orbit of radius r. So a small star is there in an orbit of radius r. Here is my small star. The period of revolution of this small star r will depend upon. Now inside this region there will be mass. Let us take that mass is m. The force on this small star on this direction, in this direction, how much it will be? That is g into mass of total mass inside into mass of this small star divided by r square, and this is m into v square by r. Perfect. Mass into centripetal acceleration. So from here v comes out to be root of gm by r, and the time period 2 pi r to the power 3 by 2 by gm. It is coming like this, the same derivation. But I need to put this m here. What is the total mass in this sphere of radius r? For that I need to do integration. At a distance r from here, I will consider a small shell whose thickness is dr, the mass of that as dm. So my dm will be the density there, k by r, into the volume. What will be the volume? Surface area into the thickness. Surface area is 4 pi r square into dr. Okay, so this is 4 pi k, r integration will become r square by 2, r square by 2. Okay, this is my mass m, limit will go from 0 to r, capital R. So this becomes 4 pi into k into r square by 2. Anyways, I can say this as 2 pi k r square. Put it here. I need just the proportionality, r to the power 3 by 2 divided by root of m. If I do, this will come out to be r. So t is proportional to r to the power 1 by 2. It means t square is proportional to r. T is proportional to r to the power 1 by 2. So t square is proportional to r. Option B. Is this clear? T square is proportional to r. Okay. No, don't remember this. T square is proportional to r. I'm just deriving the. Try to understand how I wrote the equations. The relation came exactly. I would have written directly also, but I was just showing it. So this is the relation. Okay. Here, but the variable is m. Okay. M is variable. So putting that m by finding the total mass inside of the galaxy inside that region. So I got that. Another question, let us read it out. This is the energy required to take a satellite to height h above the Earth's surface is even. Okay, so let us consider this is my Earth's surface and you are taking the satellite above a height h here, and the energy required is even. So how much energy you are taking that slowly? Okay, so how much energy? That energy is equals to change in potential energy. Final potential energy is minus gmm by r. Total distance will become r plus h minus initial potential energy, so plus gmm divided by r on the surface. From the surface I am taking to height h. I found the change in the potential energy, that is the energy I need to give. So this becomes my E1. And the kinetic energy required for the satellite to be in circular orbit at this height is E2. Now, when I am moving this in the circular orbit here, how much is this velocity? V is equals to root of gm by r, that is r plus h. Okay, that is the velocity. I can write the kinetic energy here. So E2, that is my kinetic energy, that is half into m into v square, so that is gm divided by r plus h. Okay, the value of E1 and E2 are equal is the value of h for which the value of E1 and E2 are equal. So equate these two things, equate this. So I am putting E1 equal to E2. I am doing E1 equal to E2. So gmm by gmm by r plus h with a negative sign plus gmm by r is equal to gmm by 2 into r plus h. Writing it. Now you can take this term to the other side, and that will become 3 by 2 times of that. Okay, so let us do here itself. So just rubbing it and putting here 3. Now gmm got cancelled, 3r comes out to be 2r plus 2h, so h comes out to be r by 2. H comes out to be r by 2. R is 6.4 into 10 to the power 3 kilometer. So r by 2 is 3.2 into 10 to the power 3 kilometer. Okay, simple concepts, easy questions. Now let us talk about geostationary satellites. Geostationary satellites, as the name suggests, geostationary. They appears to be stationary from the surface of Earth. Okay, or they remain stationary with respect to Earth. The time period of Earth revolution is 24 hours. The time period of these satellite is 24 hours. Okay. So this is Earth. This is the equator. So the geostationary satellites are in the equatorial plane, moving like this around the Earth in the equatorial plane. At a certain height, like when the r is changing, the time period is changing. So at a particular value of r, the time period will be equal to 24 hours, isn't it? Yes, that is possible. And these satellites are moving in the same sense as that of Earth. So what happens is, this is Earth, this is Earth, this is particular satellite, okay, this geostationary satellite. This will be always above, let us take, this is some region on the Earth, some city you may say, okay, this is above that city. Now Earth will rotate, this city will go like this. With the same angular velocity, this satellite is rotating. So always if you see, for that city, the satellite is just always overhead, isn't it? So these type of satellites are used for communication purposes, for television, okay, live telecasting, all these things, okay. So you see that these satellites can cover this much region. Like if this satellite is there, it can cover from here to here, this much region it can cover. So similarly, like we have multiple satellites, so that we can cover the entire surface of the Earth, or entire region that we want to cover, okay. So anyways, we need not go into that much detail, that is not required for us. The important thing here to understand is the time period of this geostationary satellite. Oh, where it is, the slide changed. Oh, so that important thing to understand is the time period of this satellite is 24 hours. So time period formula is 2 pi r to the power 3 by 2 by root of gm. This is 24 hours. From here you can find r also. How much is r? And this r nearly comes out to be 7 times of radius. So the height of geostationary satellite from the Earth's surface is nearly equals to 6r. I am not telling exactly, nearly, okay, nearly equals to 6r. They rotate in the same sense, and their angular velocity is equal to the angular velocity of Earth. Only then only they will remain always on the, you can say, on the same city. Their angular velocity need to be the same, the sense need to be the same, okay. Therefore they appears to be always stationary with respect to the Earth. Therefore we say them as, these are the geostationary satellites. Now in Earth, this combination is there, like it may happen for us, for a planet to may not have a geostationary satellite. How? Like if numerically it comes inside the planet, what happens? Cannot have, isn't it? But for Earth it is possible, like the density and the radius is such that we are having a geostationary satellite, and which is at a decent height, not very far away also, okay, and not even, you can say, if numerically it comes less than r, the radius of this, what happens then? Then geostationary satellite won't be possible. Anyways, that was some side stuffs. Okay, coming to the questions. A satellite revolving around a planet in stationary orbit has time period 6 hours. Okay, a satellite revolving around a planet in stationary orbit is having time period 6 hours. Now this is for another planet, certainly for Earth it is 24 hours. The mass of the planet is 1/4 the mass of the Earth. The radius of the planet, the radius orbit of planet is, okay, what is the orbit of that radius of the geostationary satellite? Here it is given, the radius of geostationary orbit for Earth is this much, that is nearly equal to 7 times of Earth, okay. So that radius is 4.2 into 10 to the power 4 for Earth. How much will be that for that particular planet? So if I write the time period formula, time is basically 2 pi r to the power 3 by 2 by gm, root gm. What is changing? R is changing, M is changing, T is changing. Okay, so I'll say that T is proportional to r to the power 3 by 2 by root m. Okay, so for Earth, if I write time period is 24 hour, proportional to the radius for Earth, geostationary radius for Earth is 4.2 into 10 to the power 4 kilometer. I am putting that in kilometer only, to the power 3 by 2 divided by root of mass of Earth. For that planet, it is 6 proportional to radius we need to find for that planet to the power 3 by 2 divided by mass. Mass of the planet is 1/4 the mass of Earth, root of m by 4. So root m is getting cancelled, divide these two, 6 into 4, root m is getting cancelled. What else? Root 4 will become 2, okay, and this 2 will go in the numerator and it will cancel this, isn't it? Am I saying right? This is root of m by 4, okay, this 2 will go here, not there. Anyways, so this 2 will be here and this will become 8 there. Okay, so 8 is equal to 4.2 into 10 to the power 4 to the power 3 by 2 divided by r to the power 3 by 2. Let us take whole to the power 2 by 3 both sides. So 2 by 3 of 8 will become 4. So 4 is equals to 4.2 into 10 to the power 4 divided by r. R comes out to be 4.2 divided by 4 into 10 to the power 4, and this comes out to be 1.05 into 10 to the power 4 kilometer. 1.05 into 10 to the power 4 kilometer. Yes, D is correct here. Okay, we related time period with R and M. For Earth satellite, we know time period is 24. Geostationary satellite, for that planet, time period is given 6 hours. Okay, for Earth satellite, the distance is given for us. For other planet, we need to find R. We found it. Now, weightlessness in a satellite. Now, in space, if we see the satellites are moving, let us take in a circular orbit. Okay, I'm taking for circular, you may take another also, elliptical also. So, let us take a satellite is there moving around Earth. It is only under gravitational force. There is no other force, that is only force due to Earth. So, it is in a free fall condition. If it is in a free fall condition, weightlessness will be there. Yes. If let us take some lift is free falling, you are inside the lift, you will feel weightless. Okay. So, during free fall, the weightlessness condition will be there. But if we want to prove that mathematically, we can write. Let us take this is the planet. And let us take a different color, and the satellite is moving in a circular orbit. Around this planet. Let us take here is the satellite. Now, the force due to this planet, okay, let us take the satellite is moving with some speed v. So, inside the satellite, I am drawing now. This is my satellite, okay. I am zooming in this satellite, I am drawing the image. This is inside the satellite view. Here is an astronaut. Okay. Now, this astronaut is moving in a circular orbit, certainly like this. The radius is r of the circular orbit. It is moving at some speed v. I am considering, let us take it is having some weight weight means it will be having some normal reaction due to from the satellite. Let us take normal reaction. This is force due to gravity. How much is that? Force due to gravity, G, mass of Earth, mass of this astronaut divided by r square. Okay, and it is having an acceleration, centripetal acceleration towards this is centripetal. So when I say this force minus the normal is equals to mass into centripetal acceleration. So G m by r square minus n is equals to mass into the centripetal acceleration, that is v square by r. Clear? Now put v. What is the velocity of this astronaut? Velocity is equal to the velocity of satellite. Velocity of satellite is root gm by r. So this will become just gm by r. Root gm by square is gm by r. And comes out to be 0. It will feel weightlessness. Okay. This is my Earth. The astronaut will feel weightlessness, and from common sense also we can say, as it is in a free fall condition, he should feel weightlessness. Now let us discuss this question. An astronaut is in an orbiting space station above Earth, experiences weightlessness. Yes, this is true. This is true. An object moving around Earth under the influence of Earth's gravitational force is in state of free fall. Yes, this is also true. We already discussed that. This is also true. And this is the reason due to which it is feeling weightlessness. So I'll say statement 1 is true and 2 is correct explanation of statement 1. So statement 1 is true and statement 2 is correct explanation of statement 1. Yes, A is coming out to be the correct option. Now let us discuss about Kepler's laws. So we have 3 laws. First of all, the first law. What is that first law? All planets move in elliptical orbit with the sun being at one of the focus, okay, of the ellipse. So we, as in maths you would have studied, ellipse has 2 focus, okay. So this is one and here would be another. So sun being at one of the focus, okay, and the planets are moving in the elliptical. So elliptical orbit has one major axis, another minor axis, okay. So this is my major axis 2a, this is my minor axis 2b, this is my sun, and let us take the planet is moving like this around the sun, okay. And the first law states that that orbit is not circular, that is elliptical, okay. And before that it used to be understood that they move in circle. Now the second law states that, this is the law of areas, it states that the line joining the planet and the sun, this is my sun, this is my planet here, the line joining the planet and the sun, this sweeps equal area in equal interval of time, okay. Let us take in 1 hour, the area it will sweep here, it will be same as it will sweep area on the other side for 1 hour, the area will be same. Means if I find the rate of area swept, dA by dt, that is constant, okay. Let us try to find. My satellite moved from this point to this, and let us take this arc is making an angle theta here. This is r, okay, this is nearly r only. So this I am saying this arc is having nearly r d theta length. The area of this, you can say this is a triangular kind of strip, that will be 1 by 2 into base into height into r d theta into r, height is nearly equals to r, okay. This becomes my area, this is my dA, and dy by dt, d theta by dt becomes my angular velocity omega. So this will become omega square r by 2, multiply with m, divide with m, this becomes my dA by dt, m omega square becomes my moment of inertia, okay. What is that? Moment of inertia, I did a mistake there, not m omega square is not moment of inertia. Mr square is the moment of inertia. Sorry, I did a mistake. This is r square. D theta by dt is my omega. Okay. So this is 1 by 2 into r square into d theta by dt is my omega. Yeah. And this is my dA by dt. Multiplying with m and dividing with them. Now mr square becomes my moment of inertia. This becomes I omega by 2m. That becomes my angular momentum. So dA by dt comes out to be L, the angular momentum, divided by 2m, where m is the mass of the planet, small m. Now, about the axis passing through the sun, the angular momentum is constant. Why so? Because the torque is 0. The sun is having a force along that axis only. So the torque is 0. If torque is 0, angular momentum is constant. Okay. If my torque is 0, my angular momentum is constant. Angular momentum is constant. Therefore, I can say that this L is constant, mass is constant, so this comes out to be constant. So rate of area swept, that is dA by dt, that comes out to be L by 2m, and that is constant. That is not changing. Clear? One more thing. Yeah. As the planet, because the angular momentum is constant, as the planet is farthest, the speed will be minimum. As the planet is coming near, the speed will be maximum. This is my perihelion, this is aphelion. Okay. So when the planet is farthest, this will be my minimum velocity, and when it is nearest, this is my maximum velocity. Okay, and angular momentum is conserved. So you can say if this distance is r1, this distance is my r2, my m1 into v1 is vmax, what I am writing, my L1 is equals to L2. Okay, so what is L1? M into vmax into r1 is equals to m into vmin into r2. Because angular momentum is conserved, I can write like this. Okay, now coming to some questions on this quickly. Let us read. The maximum and minimum distance of a comet from sun are this and this. The speed of the comet at the nearest point is this. The speed at the farthest point is. Okay, so m v1 r1 is equals to m v2 into r2. This I am saying for near point. This I am saying for far point. Okay, so for near point, the velocity is maximum. Okay, the maximum and minimum distance. So this is the maximum distance, this is the minimum distance. Maximum is 1.6 into 10 to the power 12. Minimum is 8 into 10 to the power 10. Perfect? Yeah. M is getting answered. What is, if the speed of the comet at the nearest point is 6 into 10 to the power 4, and speed here I need to find. Now here I can say 10 to the power 2 will get cancelled. This will become 10 to the power 12 is getting cancelled. 10 to the power 2 will remain here. So this is 8 into 6 into 100 divided by 1.6. This becomes my V. So 8 into this is my 0.2, so 2, this becomes 1000, 2 into 3, this becomes 3000. Okay, 3000, so 3 into 10 to the power 3 meter per second. Getting it? Okay, so just consider the angular momentum. Nearest point, the speed is my maximum. Farthest point, the speed is my minimum, and minimum speed comes out to be 3000. Okay, everything is fine. Yeah. Another question, let us read it out quickly. The angular momentum of a planet of mass m moving around the sun in an elliptical orbit is L. The magnitude of aerial velocity, we already derived that, that is L by 2m. That is L by 2m. You need to remember that. Here m is mass of the planet. Okay, now Kepler's third law. This is law of period, and for satellites we saw that t square was coming to be proportional to r cube, and the same relation is followed here. Okay, so the square of time period of revolution of planet is proportional to the cube of the semi major axis. So you need to remember t square proportional to a cube. Coming to question, a planet takes 200 days to complete one revolution around the sun. One revolution around the sun means time period is 200. If the distance of the planet from the sun is reduced to 1/4 of the original distance, how many days it will take? Now t square proportional to r cube, or I can say t proportional to r to the power 3 by 2. If the distance of the planet from the sun is reduced to 1/4, so my t dash is r by 4 to the power 3 by 2. What is that? R to the power 3 by 2 divided by, this will become what? 4 to the power 3 by 2 is 8. Yeah. So t dash comes out to be t by 8. So time period will become 1 by 8. So this is 200 divided by 8. How much is this? 4 into 2, 50. This is 25. Okay. So we are getting that the time period will become 25 days. Now the homework for you, and that homework is in the link that is given in the description. From when you click that link, you'll go to our app, you'll join the free batch there, and there you can access the assignment, or I'll say the DPPs, the practice sheets, okay, for this particular topic. And those questions are the questions which are having the same type of varieties which are asked by NTA. And I can say if you practice those questions, you'll be able to revise all the concepts that we have discussed in this class. I tried to cover all the varieties of questions till now. Different varieties of questions were there in each of the topic, and I tried to consider all the varieties, and with, you can say, great explanation, we have covered each topic. So now you have watched, you have come till here, make sure you comment completed in the video, and you go in the link in the description box, open that practice sheet and solve this after this video. So thank you all, have a nice day.